Good afternoon, everyone. So hope everyone enjoyed morning session. So this afternoon, we will start with the topic about how to 10 times AI agent price, performance with inference time scaling. Jared Clancy Davis will present this insight. Jared is the CEO from Foundry company, and let's welcome speaker.
Performance, but in terms of quote-unquote chain of thought at 32 performance, right? So they were basically making 32 parallel calls and then had this kind of, somewhat Byzantine scheme to combine those results and pick a final answer. And people thought this was cheating. They're like, oh, you shouldn't do this. Google was like, no, this seems like a reasonable thing to do. Seems fair. And actually they're making some good points. Like depending on the size of the model, actually it might have been less total compute, right? That was actually part of a much longer intellectual lineage, actually, at Google, that I actually give DeepMind some of the first credit for doing something that looks like compound systems with AlphaCode. So they released AlphaCode at the end of 2022. It didn't get much attention because this is also when ChatGPT was released. Everyone was pretty focused on that. But it was a really, really interesting method that they had undergirding AlphaCode where they actually beat humans at coding competitions. And the way they did it was by making 1 million parallel calls to what at the time was a state-of-the-art kind of multi-hundred million parameter model. 1 million calls at once. They would ask the same question to 1 million replicas of the model. And they had this kind of interesting protocol for filtering down to the top 10 responses and then running those one by one until the test passed. It turned out this worked really, really well. It's kind of a funny scheme, but it worked. And this, this idea, this kind of concept, has compound systems has broadened beyond, though, just composing ensembles to other schemes. This is one of the first instances of work on routing, which is very intuitive. Everyone does some form of this probably in production in your companies and in your work. Is this early work on Frugal GPT was looking at, okay, well, it turns out there's some notion of an intelligence level that you can saturate with a small model, right? And so you don't always need an Einstein-grade model to answer simple questions. Turns out you can just if the question is a simple question, which turns out it's actually easier to judge the difficulty of a question than to answer the question, or easy, I'm using that term liberally. It's true in terms of number of tokens, it's true in terms of amount of compute, it's also true in terms of the intelligence required by the judge to classify. By doing that, the system was able to be 98% cheaper than GPT-4 with equivalent performance on a number of evaluations. So that's pretty exciting. And this was just based on just these two models, GPT 3.5 and GPT-4. That idea started to get a lot richer, though, and so now it's becoming clear that there is a very rich architecture landscape of these compound systems. You can actually take these inference calls and build architectures out of them, just like we build architectures out of neural networks, right? And we talk about how many parameters are in a neural network. We talk about whether these are recurrent structures or et cetera. But I think something similar is starting to emerge at this kind of networks of networks level. This is one of the early works on this. R more LM calls all you need. A very funny naming scheme. And this was looking at, okay, if you want to go beyond the kind of quality and reliability frontier accessible by today's state-of-the-art models, to what extent can you do the naive thing of just making N calls, let's say 1,000 calls, 1 million calls, to whatever the current state-of-the-art model is? To what extent can you do that and get GPT-7 performance early out of GPT-4? If you're willing to pay a higher price, right? If I told you that I'm budget insensitive, that $3 per million tokens is too cheap, my answer only requires a few tokens, I'm willing to make 1 million calls, to what extent could I do that and, in the most naive sense, actually get better performance? It turns out even this very basic scheme there's a lot of richness and nuance in the dynamics that arise here. So for example, turns out there are kind of these non-monotonic scaling curves that arise where as you increase the number of calls, you don't necessarily get better performance. Actually, performance can go down. And I'll come back to that, actually, if that's interesting. Performance can go down as you make more calls, but in a way that we can foresee and predict. This then spawned work on, so that was the most basic work there was on, you have some ensemble and you're just doing voting-based aggregation. So you're taking the most common response. Well, what happens if you have judge-based aggregation and some type of verifier-prover structure? What happens there? It turns out this has its own dynamics. You can characterize these systems in the same way that people often characterize kind of cryptographic systems in terms of, for example, I'm not sure if people are familiar with PCPs, but these kind of probabilistically checkable proofs these types of structures, where you characterize them in terms of the kind of proving complexity and the verification complexity. And so there's almost like a GAN-esque idea in how you can compose these systems and kind of get better performance. And so quite a bit of richness. I'll just sample a few more works and show broadly like why this area is interesting, try to characterize this as an area. Here's some work on DSPy. Everyone's probably heard of DSPy from our lab. DSPy was kind of one of the first frameworks to try to systematize building LLM programs where you could actually try to backprop through and optimize the prompts, right, by searching in the initial constructions, just kind of searching over potential prompts, and adding, all these kind of tricks that we've all learned, like, hey, model, I'll give you a tip if you behave or if you give a good response, like kind of iterating over those types of tricks, injecting them intelligently, or just more freely backpropping through proofs. Here's another compound systems idea, just to complete the survey. The model families concept, where now every generation of these models has a large variant, a middle-sized variant typically, and then a cheap variant that's kind of cheap and fast inference. And in this agentic context, this is more and more important. Like, you don't want to use the big, slow system on, kind of just parsing through websites and opening up browsers and clicking around, et cetera. That's very wasteful. You want kind of specialized models that can do that very quickly. So here's, I think, where things start to get really, really interesting, which is, I think, when these ideas started to really make their way into the kind of really common conversation in our field, is with the inference time scaling results. The initial inference time scaling results from OpenAI and the O series of models was actually kind of vertical inference time scaling, vertical kind of chain of thoughts. And so what you're doing is you're basically taking the same model, a single replica by default, and you're basically just unfurling longer and longer chains of thought. You're giving it the ability to make longer and longer chains of thought. And implicitly, at least, these models are doing some type of grid search within the token space. Kind of like vertically with one worker, so to speak. When you put it that way, it sounds like a super inefficient thing to do, actually. But that's actually what we're doing. And so if anyone's looked at the traces from like DeepSeek, you'll see that DeepSeek and all these other models, they'll often say wait, and they'll backtrack, right? And they'll be like, oh, I guess that's not the right answer, and they'll go back. They'll say, let me go back. They kind of make it so they're actually doing like a beam search or a tree search within the token space. This is very demanding, though. It requires a ton of HBM, a ton of GPU memory. And so it's challenging. It means that you need basically a state-of-the-art server to run one of these models. Or you have to do some type of model parallelism. You have to split the model across at least a couple of chips. That means it's kind of cost prohibitive to do. But people have taken these ideas, and reasoning works. And so it turns out people have been using it applied to a bunch of different agentic settings. Here's one of my favorites, the virtual lab work by James O. At Stanford, constructing these compound systems with different agents, with different personas, and getting them to kind of work through tasks. So I'll skip forward a little bit. The point is there's a lot of different work going on that can broadly be called compound systems. And we've actually chronicled some of these. And if people want to add things that you like, you can add them to this repo. This awesome compound systems repo that's going to be affiliated with the conference that myself and some other Berkeley and Stanford people are going to organize. Oh, I'll go back to that. I saw some people taking photos. I'll let you do that. You can contribute to the repo. So next, I'll just give a perspective on why I think this area is so important, and then we'll talk a little bit about some frameworks for taking these ideas and actually using them to address your problems, and kind of talk to the audience about what types of problems are you working on. I'll go forward there. We'll come back to that as well. OK, so crazy slide. You already saw it, so I'll just go into it. So first, I want to step back a little bit before I make this next set of points. And I want people to just reflect on just how ludicrous the deep learning hypothesis is, and how remarkable it is that this kind of works. Right? So if you talk to some of the early pioneers in deep learning, so I was on a team at DeepMind before starting my company Foundry. That's called the core deep learning team. And our team was actually very controversial. A lot of people weren't that enthusiastic about deep learning. It's funny to remember that, even just a few years ago. And the deep learning hypothesis was very hand-wavy. It was almost dissatisfying in some ways, but it's very intuitive and simple, which was basically, everything that we call intelligence comes from these kind of systems of neurons, that are composed of what we call the brain. The human brain is, the best existence proof for general intelligence that we know of. And so the idea was, OK, what if we can construct, it's very simple, just like if we can construct artificial systems of neurons, build them out of sand. It's kind of crazy that this works. We build these artificial systems of neurons. They're built out of silicon. They're built out of sand. We run a ton of power through them from these power plants and solar panels. And like somehow, actually, turns out that does replicate, at least at the surface, does actually simulate many aspects of intelligence that we care about. At least declarative and procedural knowledge to a great extent. It's kind of wild that this works so well. Obviously, this requires, though, that these artificial systems of neurons get bigger and bigger, that we can get closer and closer to approximating the brain. This is at least the intuition that people like Ilya and Jeff Hinton and many others had going way back. And so now I'll kind of try to extend that intuition and talk about these networks of networks and give you some sense of why these things work. So stepping back and giving just a bit more context, a lot of deep learning's progression has been about bending the curve on scaling dynamics, right? We have these magical principles, of the universe that we discovered, these kind of scaling dynamics, where you build these larger and larger systems of neurons. There's a Kolmogorov explanation for these things that we can go into, but you get the idea. You have these larger and larger systems, and part of the point has been, okay, as we throw more and more flops, more teraflops at these systems, to what extent do we get intelligence out, right? And a lot of research is bending the curve on that dynamic, ensuring that you get greater efficiency out of incremental flops, right? Greater intelligence out of incremental flops. And so the first era, was kind of the pre-2012, pre-GPU era. We saw compute scaling pretty dramatically for these kind of older neural network-based systems. And then since 2012, obviously, we've seen things inflect. And if people saw Bill Daly's keynote earlier, you'd know that things have inflected once again since the transformer era in 2017. And now things have inflected once again with these inference time scaling systems. So I'll talk a little bit about that. Here's another angle for looking at this. This is basically an efficiency curve. Let me go to the next chart so you see it a little bit better. At the same time as we've had compute scaling dramatically, as we've been putting kind of doubling the number of petaflop days or teraflop days in these systems every 3.4 months or roughly, we've also seen training efficiency go way up. So it's been inflecting up. We've roughly been getting a 2xing of the efficiency of these systems every 16 months. And so these two trends overlapping is leading to kind of the acceleration of progress. The really exciting thing is now with this inference time scaling, we're seeing the first version of this search idea is applied to the kind of intelligence gain that we get out of scaling these systems. So this is, I think, the best initial example and anecdote of how we've started to bend the curve on the amount of intelligence we get out of additional flops. So there's an annual poker competition. And there's a really cool story from this, which is AI poker was kind of one of the holy grail challenges. It's a kind of a hard game. It's partially observable. It has a lot of property, a lot of desiderata that you want out of a hard kind of game regime. And these systems were getting better year by year, largely by just increasing the number of parameters. So roughly what you see on that chart, it's on a log scale, as you see exponential increase in the number of parameters in these poker playing systems. This is some great work from Noam Brown. And something really interesting happened where they'd been kind of on this curve of progress, increasing number of buckets, which is roughly number of parameters. And the blue line corresponds to just standard kind of pre-training scaling. It was progressing really nicely. But then there was an observation that Noam and some of his collaborators made, which was the AI system, even in really tricky, hard scenarios in poker, it was always moving instantly, whereas the human opponent would take a long time to think. The human would pause and be like, okay, this is a challenging scenario. Let me think about this, right? And it's a common parameter in game-playing systems like Stockfish to have like a thinking time parameter that you can adjust, right? Because these are search-based systems. Well, the poker-playing bots didn't have that. And so Noam, in this paper that I'm showing below, they introduced search, which is another way of saying inference time scaling, on top of these poker-playing systems. And you immediately saw, roughly speaking, the lower you are on this chart, the better. They immediately saw this massive shift downwards, to the point where you would have needed to 100,000x the scale if you were in this blue regime to intersect with the end point of this orange regime. And so that was just a massive inflecting, a massive bending of the curve of progress, of the amount of kind of the return to additional compute. And you see this now in a more general way in these inference time scale kind of general transformers, GPT type systems, where this was the very controversial result from very, I think, got a lot of people's attention in the O1 announcement, just adding compute, adding additional flops on a logarithmic scale, funnily enough. So it's actually a kind of a tapering off curve. And yeah, you get greater and greater pass-at accuracy. And it's funny because now this is basically what Gemini was doing back with Gemini Ultra, with the chain of thought 32. In some sense, just along a different vector. It's ironic that now this is the regime, and Gemini doesn't kind of get credit for starting to pioneer this a bit. All of this is actually part of that same bitter lesson, in some sense, right? The classic bitter lesson, that search in general learning, kind of methods that can assimilate compute, are really important to pursue. I think part of the intuition of deep learning, to put it a slightly different way, I noted that kind of crazy intuition about the human brain, et cetera. When I talk to some people who were kind of there at those earliest days, another thing I hear quite often is they had intuition that deep learning would work well because it was clear to them that deep learning was one of the ML theoretic regimes that would best be able to assimilate compute. That Moore's law is kind of the greatest trend ever. Compute scaling, what we've seen is the greatest exponential that civilization has ever witnessed. And so you want to kind of pursue methods that can ride that wave as much as possible. And that intuition was really, really powerful. So now you have a little bit of grounding of, okay, you want methods that can assimilate compute well. You have some notion that there's different dimensions along which you can scale compute. You can scale it vertically with deeper chains of thought. You can scale it horizontally with more replicas. There's different things you can do. There's scaling dynamics. You can kind of have systems that route among models and kind of use compute efficiently that way. You can have ensembles. So you have some intuition for that. So now we'll jump over and talk about some of the ways that you can actually start to use this intuition and bring this to bear on your problems today, but then also maybe some ideas that people can take with them if you're doing research or trying to expand the frontier. OK, so let me talk a little bit about ways to put these intuitions to work. So, and I apologize for those who were at the talks this morning. You're going to get to hear the same talk twice, parts of it. I apologize for that. And you also get to see me try to navigate. OK, perfect. Yeah, so I'll talk about, OK, so how do you actually start to bring some of these things to bear? And so it's very difficult for academics or people just in regular industry to push that kind of RL, deeper chains of thought frontier. It's very, very expensive. These systems are hard to wrangle. They're hard to understand. But people have been doing a lot of work kind of building routers, building ensembles. That's a very common pattern. Many of you are probably already doing that in your work. One just most common primitive is if you have a problem that you need a reliable answer for, people will often just call multiple models on that question, 2 times, 3 times, 4 times. And then if they all concur, if they all have the same answer, you can probably feel pretty confident that if you independently invoke them and they agree, it's probably not a hallucination. So I've met many, many companies that have some version of this pattern in production, where they have multiple models, do some type of document extraction or whatever it may be, some translation. And if the answers concur, they send that answer along down the funnel. And if the answers diverge, they invoke a BPO or bring a human in to kind of check the answer, right? Which takes a lot more time and is more costly. It makes their business model inviable if they have to do that for everything. And so what we want to do with this system Ember is we've been doing a lot of research, some of which I showed earlier, on constructing routers, on constructing ensembles of various types. And this type of research can be a little bit painful to do. There's a lot of kind of pipe building work, not the most glamorous. And so we just want to build a common research framework that all of our collaborators across a variety of companies, Microsoft Research, IBM Research, NVIDIA, Berkeley, Stanford, Google, Foundry, could use. And so that's what Ember is. And so we call it an inference time scaling architecture framework. All right. There we go. Yes, so I won't go, at this point I made earlier, but I'll just reiterate it because it's so important. We found that by combining calls to these models, you can get GPT-7 early, so to speak, if you're willing to pay the price. It might not be very cost efficient, but you can kind of get a much higher performance really, really early, arbitrarily at inference time with kind of inference time scaling. It's actually, by the way, even better if you can do this across models. These models have their own affinities. They're good at different things. Google's models are better at some things. Claude is better at some things, like agentic coding. It's famous for that now, right? Some of these models have their own personality. You can combine them across providers and actually get boosts across tasks in some really powerful ways, especially in agentic settings when you decompose things. So that's improving the quality reliability frontier, but you can also improve costs. So some of the cheapest systems are 1/5,000th what some of the more expensive systems cost. And so you can make 5, 6, or more calls to some of the cheaper systems and still be 70, 80% cheaper than the quote-unquote frontier systems. So we've used these ideas and gotten really, really great results in a number of agentic tasks and published works that have recently won best papers and crossed a number of these recent conferences like NeurIPS and some of the workshops. Yeah, so this is the framework. It's shared for research across a number of different groups. And a lot of papers actually based on these ideas will be coming out over the coming weeks and months. And you also hear about a new conference that we're starting with the ACM that you'll hopefully hear about very soon. That will be kind of a flagship conference on agentic systems and compound systems. OK, so I'll just skip through some of this since we talked about it. The only point I'll make from here is I think today when we talk about these systems, even when we're talking about these ensembles, the original Gemini example was 32 calls. It was chain of thought at 32, right? In the more extreme cases, you might make 1 million calls, 1 billion calls. And so in the future, when we talk about an 8B system, we might not be talking about the number of parameters. We might be talking about the number of calls in some inference time architecture. That's kind of a funny thing to imagine today, but I think we're not very far from that at all, particularly in these agentic contexts. And that's possible and tractable because the cost of inference is falling precipitously, and a whole host of people, from clouds like us to hardware companies like NVIDIA and Groq and AMD to companies working on distilling models, new methods for distillation, across the entire spectrum, people are working on pushing this further and further and further as like kind of a new Moore's law of our era. And yeah, there's more and more models. I think it was unclear to people a year ago whether we were going to end up in a regime with models that looks more like radio, where there's kind of 3 or 5 stations, or something more like TikTok, with kind of a vast ecosystem, a long tail of models and fine-tuned variants and distilled variants. I think the evidence is actually increasingly going in favor of this kind of much more menagerie of models kind of future, where there will be many, many distilled variants, many, many post-trained variants, many, many kind of heads, et cetera, and more providers. I think that's becoming more and more evident. OK, so I'll skip forward a little bit. Sure.
Why do you have two Groqs highlighted with arrows?
Oh, that's actually just from the Groq. This is from artificial analysis.
I thought you had something
Oh, yeah.
about reasoning.
Yeah, I'll repeat the question. Yeah, so the question was, why are Groq models highlighted here? So this is actually from artificial analysis. And it was partially highlighting this kind of notion of a Pareto frontier, where these Groq models are, if you look here, there's kind of this notion of how intelligent is it versus how expensive is it. And Groq models are actually in some pretty attractive, at the ends of the spectrum in an attractive way. So Groq 3 mini reasoning is very, very cheap, but very, very intelligent. And so it's kind of highlighted by this independent reviewer, artificial analysis, for being really, really strong. And the Groq 3 is also quite strong in intelligence and also quite cheap. Awesome. So I'll skip forward a little bit. This kind of just highlights some of the work that I talked about, how this observation that the cost of inference calls is falling has motivated lots of interesting work. I'll skip that point. All right, so that motivated us to create this framework Ember that I'll talk a little bit about today, give you guys some intuition about, which was just trying to make it easier to construct these types of graphs, share them. A really, really important part of why progress was so fast in the 2010s was people could build modules, build architectures, do research, and then they could share the work that they did, open source, and then people could start not from scratch if they had some new idea. You could just download, hey, someone else did this idea, I'll just take the code, git clone it, and then I can immediately make some tweak, and get a new paper out of it. Right? That type of thing was really important. That's how you get exponential progress. Right? Things kind of stack. If everyone's starting from scratch, you don't get exponential progress. So that was Bill Daly's point about programmability and compositionality, the point that Daly made earlier. So it's super important in this kind of inference time scaling context. And so you need some notion of torch for this new regime. Neural network, like perceptron research, wouldn't have been very ambitious if you were doing all the neural network computations with for loops. You would never make a graph very, very large. Like you wouldn't create these GPT kind of type structures with multiple blocks, ensemble, these kind of embedding blocks, attention blocks, FFN blocks, composed with billions of parameters. You wouldn't do that if there wasn't parallel dispatch, so you weren't running things in an efficient vectorized way on GPUs. It'd be super slow. Put it simply, it'd be super duper slow if you didn't have that. It also would be difficult if you had to write these systems in these hacky ways. People may recall doing work early on before some of these frameworks. It was very, very painful to do neural network research, right? Did anyone take Andrew Ng's MOOC way back in the day? And yeah, I've seen a bunch of nodding. Yeah, the MATLAB-based neural networks. There's only so ambitious you're only gonna be so ambitious if you're using MATLAB as your framework, right? And so part of the idea is, okay, can we start to do some work on developing what would kind of a torch look like for this network of networks era, where you're composing calls across different models, et cetera. Yeah, and the goal is, you want things to be, really, really simple and quick to express a new idea, and you want that idea to run efficiently and quickly as well. The pain of every researcher's life is waiting for experiments, and when you start to, ensemble these LLM calls, it can be super duper slow. And so, these experiments can take a while. So you want to parallelize things. You want to dispatch things all at once, especially if you're calling open source models on top of frameworks from our lab like VLLM or SGLang. You need to make sure you're getting really, really high utilization of a GPU, able to make as many calls as you can with as few resources as possible. But even for calls to these API providers, you want to kind of saturate the API, spam as many requests at them as you can until they turn you off for DDoS. That's the goal, right? I'm trying my best, right? And so, I'll give a couple of code snippets to give people intuition for how you build these systems. You might have seen this earlier today, but a lot of information is being thrown at you, so repetition is not the worst thing. Okay, so there are really three syntaxes that people have built. One is just regular functions, but then there are these kind of two syntaxes that researchers have been using. This one actually I kind of like. It's this little string-based syntax that's just an extension on top of the base framework that I'll show you on the next slide. I like it because it's just a couple of lines, and it's really intuitive to figure out what's happening with just reading a single line. So here, this is just a really basic graph defined by this just basic list with a couple of components. So the first component is an ensemble of 101 members of just GPT-4 calls, all GPT-4 in this case, with temperature of 0.7. And then the next is a judge with Claude 3.5 Sonnet and 0 temperature. And then that system becomes a graph, and then you can kind of call that like you would any other function, giving it queries, and it will kind of answer the question by passing it through this graph in a unique way. One other kind of funny point is you can have kind of cross-provider graphs as well, where you can have subgraphs, and this is also 101 models, but across providers. So you've got GPT-4o, Claude 3.5 Sonnet, Gemini 2.0 Flash, Claude 3 Opus as a judge. And you can kind of dispatch the request across different providers. Also, I'll note the GPT-4o call on the back end can also be dispatched across providers of that same model. So you can call both OpenAI first party, and if you have API keys, you can call Azure OpenAI across regions too. So you can get kind of a lot higher throughput. So instead of 10,000 requests per minute, you can have 60,000, 70,000, et cetera, at the same cost. Actually, that's an important point. One of the things about the cloud that got people at Berkeley actually really excited back in the day, if anyone read Above the Clouds of Berkeley View on Cloud Computing, was the idea that kind of fast is free in the cloud. That was the revolutionary thing. Right? The idea that if you have some job that would run for a day on 10 machines, in the cloud you could run it for 15 minutes on 1,000 machines, and it would cost the exact same. As long as it was kind of horizontally scalable. You can go 100x faster for the same cost. That was a revolutionary thing. Obviously that got people really excited about things like Spark, right? If you can kind of parallelize these Spark requests, and that set off this big wave, people trying to move things to the cloud, so you could take advantage of this, right? And that's a really important point, and you want to be able to do similar things with these inference calls. Here's a more explicit way of defining it. This is kind of more like PyTorch. You've got some typed input, typed output if you want. So you can specify this is what an input has to be, and you can also put more logic in here and have it meet some desiderata. You can obviously output as well, but the more the simple part is you can define this module, which is an operator. In this case, it's just an ensemble and judge system with a parameterizable width for the ensemble. you inject that at runtime, and you define this eagerly, right? So the forward method is written just like PyTorch eagerly, where you're just kind of doing operations in a Pythonic way. But underneath, it's kind of like TensorFlow, like JAX and XLA, in the sense that there's an IR being constructed, kind of an intermediate representation of the graph, of the DAG and the dependencies is being constructed. And that IR can be grabbed and ported. It can be moved client side and run, if you want to. It can be run server side in some intelligent way. You can lower it, you can re-optimize it, you can do interesting things with it. And that's what the JIT is doing. So kind of like JAX in some sense, you just JIT the class. These operators are all PyTree, so it flattens it to a PyTree. And then you can do things like topo sort. Like the things that basically undergird things like Megatron, undergird all these frameworks for running transformers. Otherwise transformer inference would be painfully slow. Similar concept. And then once you have that thing defined, you can call it like any other Python function on props. In this case, by the way, these operators, these are kind of from the default non-library. So kind of like nn.linear, nn.dropout, and PyTorch. You have like non.uniform ensemble, non.judge synthesis. So there are kind of base prompts that you can kind of go in and tweak. Or you can just kind of take the base prompts as you would and like not worry about that detail. Yeah, there's some other things that people use a lot. So for example, just like how JAX has VMAP functionality, so you can have a graph and a set of inputs, a batch of inputs, and you can efficiently run that batch of inputs and that graph, right? And so you want to kind of parallelize across both the graphs components and the inputs and get high utilization out of that. So it has utilities like that. It also, both in the string format and obviously in the operator format, you can also define reusable subcomponents that you can kind of name. And then those subcomponents can then become branches, kind of elements in a larger graph. So you can have a tree that is itself a leaf in a tree, right? So these kind of nested compositional structures, just like with transformers, right? Yeah, there's also this models library. I won't go too much into it, but yeah, basically you can grab an instance of a model without dealing with the peculiarities. This is actually something that the group built independent. There are some great frameworks for this now, like LightLLM, if people are familiar with that. But this is basically kind of like LightLLM. It's just if you want to use GPT-4, Claude, some local model, you can use the same API for all of them rather than dealing with the quirks of their respective frameworks where they have these funny syntaxes, .chat completions, blah, 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 right? These weird message formats. They have different names for the same variable. Some are like temperature, some are temp, et cetera. And then you blow your brains out. It's pretty bad. And then also some really simple utilities for data sets, GPQA, Amy, all these data sets people always use, parsing them from Hugging Face or wherever. These things can just be really tedious if you're trying to do research. This isn't the fun stuff. This is the drudge. And so just some shared utilities for all of that. Yeah, and as a last point, one kind of really cool thing about the system is one of the painful things about some of these frameworks is they're too opinionated sometimes. You have to write all of your logic in the language of that framework. You have to use these utilities and kind of add nodes. Well, one nice thing about the Simba framework is you can take kind of arbitrary functions, and they can be, if you wrap them with this decorator, they can be turned into operators underneath, giving a lot of great functionality around error handling, the IR capabilities, some of the execution, intelligent execution, just from like writing arbitrary functions. And you can also use arbitrary functions inside of operators and vice versa, and it handles that pretty gracefully. So you don't have to use that kind of operator class. If you don't want to, you can just write normal functions, and it will construct a class if you just wrap. Yeah, so that's basically it for sharing that. You get the idea. A lot of interesting work going on. I'll highlight a few things that different people are doing. So at least that I've been told I can highlight. There's a lot of interesting work on using these compound systems to generate novel data, kind of almost within the RL loop, generating reasoning traces, generating synthetic data. Alan and Parth have been doing some of that. Omar has been doing a lot of work on optimizing prompts for these compound systems, which is actually really interesting. It's almost like these compound systems are like agentic companies or agentic organizations. And so, one common paradigm is you can have agentic manager, agentic workers. And the question is like, okay, what should the prompt from the agentic manager to the workers be for the workers to be most efficient? And should you have different prompts for different workers? Like, it kind of gets really fun. And DSPy, which Omar built, optimizes that for kind of single model calls, but then extending that idea to these systems of model calls increases the dimensionality a lot and gets really, really interesting. Yeah, a lot of interesting work on, on kind of, I'd say methodological work on using these compound systems for understanding uncertainty from these models better. These models aren't yet perfect at having a calibrated sense of their uncertainty, and so that's what we talked about earlier with building ensembles. You can get a sense for how much the ensemble members disagree. The kind of entropy across answers is a really good signal for whether you're going to get a good answer or whether it's going to be gibberish, and it's kind of hallucinated just to make you happy. So there's work on that. There's work on, and there's a lot of applied work. There's work on running these things in batch mode more efficiently that Deepak and NVIDIA has been doing. There's work on science. So a lot of interesting work across a number of areas. All right, so that's basically it. Yeah, feel free to reach out to me, by the way, if anyone's working on cool stuff. I or others in the community would love to chat about what you're dealing with, what type of agentic systems you're trying to build. If you have ideas for how to make these general methods better, that's also awesome. So yeah, ping me, and we'd love to chat. And I'll be a router node, but there are other people in the group, in this group, that if you want to talk to them, let me know, and I can loop them in or route to them. And there's a lot of other people that are on here as well. They're doing really awesome stuff that, and connections to be made. Whatever problem you're dealing with, probably someone else is dealing with it too, and they may have figured it out. There's many, many cases like that. And that's one of the most fun things to do is like connect someone with someone else who figured out the problem they're trying to work through. That's really rewarding. Okay, I'll make this controversial point again because I like to make it, and it's like a PSA. I really want us to stop calling these things agents, without at least referencing this kind of original definition of agents, right? So this is a good time to mention this. The winners of the most recent Turing Award were Sutton and Bartow, and they won it for their contributions to RL, right? To reinforcement learning. And this is where, at least in the AI context, the initial kind of definition of an agent really, really came to the fore. And the agent was defined in terms of this framework, this kind of classic framework, where an agent is defined by its ability to take actions. It's defined in context of an agent in an environment, number one. And the agent is defined in terms of its ability to take actions on the environment. And the environment produces rewards based on the action of the agent that then go back to the agent. And it's kind of defined, so you can't really have an agent without having the agent ability to take actions on some environment, right? And there's some notion of rewards back from the environment to the agent. In this framework, there's no notion of memory. There's no notion of tool use per se. That could be one of the actions, but not necessarily. Some of these desiderata of a useful agent aren't part of the definition of an agent. They're things that we want to build really powerful agents. Just like how a neural network isn't defined by having external memory, like a neural Turing machine, that's a specific construct, right? The neural Turing machine. Yeah, similarly with these agents, under this definition, I think the original work that was done by Adept, was actually some of the original work on agents, where they had these large action models that just took in observations from pixels and then produced actions, and would build spreadsheets and such back in 2021. This was probably ahead of its time in a lot of ways. And now, obviously, we have these much more rich agentic systems. Work like Gorilla has been done to make these agents good at using tools. There's work like MemGPT that's made them good at using external memory. There's a lot of work on kind of making agents good. But I think that's these are kind of things that we want from good agents. These are desiderata. These aren't part of the definition of an agent. And so I want to separate the idea of compound systems from the idea of agents. They're related but orthogonal. Obviously, you want an agent to be reliable. And to make an agent reliable, these things around reducing hallucination, understanding uncertainty, they're all useful properties, but they're not part of the definition. So please help me in evangelizing this. It's so painful to have every academic conversation is that an agent or is that a workflow? I'm like, oh, please stop, make it stop. So you get the idea. Okay, cool. So I'll pause there. Maybe we can do some questions, and then I'll pop open a GitHub and just walk you guys through some aspects of a repo with some of the remaining time we have. And yeah, people can all clone the repo and follow it, and then contribute to it. There'll be some good stuff being added there over the coming 2 weeks. I think the 15th of August. Yes, I don't have my watch, but yes, 15th of August. Good. Okay, so let's pause there and maybe some questions and discussion.
When you build networks with
Yeah.
more complex topologies.
Yeah.
So one thing I see you mention is it leads to the possibility of comparing outputs.
Yeah.
But have you
Yes. Okay, so the question was, oh,
No, sorry.
yeah.
I remember what Andrew ever talked where he did show.
Yes, great question. Yeah, so the question was, part of this compound systems or network of networks concept, in it there's an obvious notion of you can compare answers. And so the question is like, how have you looked at measuring, comparing across answers from different models? Is that faithful representation? Okay, close enough. Yeah, so I think we've done a lot of work on this. There's a work, I was going to pull it up, but people can search it, called LLM Selector that collaborator Ling Zhao led. And it was basically looking at you have an agentic task that is defined as agentic because you're taking actions and there's multiple steps. So it's a multi-stage pipeline, quote unquote. And so instead of it being a single call, one shot, you have like 3 different steps that define some task. So it's like you first have to pull this information from somewhere, then you have to find something in the information, then you have to use that to then open some, log in somewhere, et cetera, et cetera. So it's kind of a long horizon setting. And the basic question asked there was, okay, are different models from different providers better or worse at different subtasks or at different tasks? To a very dramatic degree, and to what extent can you, by optimizing across providers, do better on an end-to-end task than if you had a single provider? And basically the result was the mixed provider system that intelligently selected the best model to do a subtask was far more effective, between at the lowest end, like 15 in the most recent variant, % better on these kind of really hard agentic benchmarks. On the high end, like 243% more effective at a lot of these tasks in terms of success rate. So dramatically more effective. And they were never worse. It was like monotonically better. Always better. And same cost or lower cost, actually, as well. Versus that kind of 15 to 243%, that's versus the best single model. So you have like 10 other models. You take the best end-to-end performance of those, and then this mixed system was doing better than the best of those. So it actually kind of shows that by combining models across providers, you can do stuff that the providers can't do themselves, which is very intuitive. But I don't think something that we appreciate broadly enough yet. And so these models are good at different things. And there's a lot of work starting to show that. I think the work from Jan Stoica and some of the LLM Arena people is really good to follow on this. They've done a ton of work on eval broadly and on LLM as a judge, and on the biases and affinities of different models. And these models are different, or better. They're different. They're better at various things, worse at various things. And that's getting more and more extreme as RL is becoming more the primary regime by which we're making these things better. In the pre-training context, we're all using the same data, right? It's kind of, there wasn't that much difference in the recipe. With these RL systems, there's a big difference, like the data mix, the shape of the RL function and the objective. Like these things are very different, and these systems diverge more. So these models are getting more and more different from each other. You actually have to make kind of almost product decisions about what you want the model to be good at and bad at in a way that wasn't really true in the pre-training era when everything was just general. So now it's getting more and more deliberate, and these models will, I think, get more and more different over time. Yeah? Yeah. You have a question? Oh, no. Okay, cool. Yeah.
You're asking the difference in multiple models, and then you're comparing like the different answers, the responses that they give. And I think there was a part you mentioned how like the cost of doing this has decreased over time.
Yeah.
And I wasn't quite sure how that would decrease because intuitively it's like if we're making several calls, that's very expensive.
Yeah. Great question. So, I'll repeat the question. The question was about kind of some of the economic implications of all of this, and how if you're making calls to multiple models, how we can say that, hey, the cost is, this is an economically efficient thing to do, and how is the cost of this? How can the cost of this be cheaper? I think the best example to illustrate this would just be this. So this is a side-by-side comparison of O1 Pro, the O1 Pro spec sheet from OpenAI, and the R1 spec sheet from DeepSeek. So R1 is a pretty good model at various things, and the price per million tokens, depending on cache hit, which is kind of a funky thing, is only 3 cents. The price per million tokens, this is input tokens, the price per million tokens of O1 Pro, $150. Right? That's a big dispersion. That's 5,000x dispersion. You can make a lot of, these R1 calls for the price of a single O1 Pro call. And that, by the way, is per token. These models are also different. They're verbose to different degrees. Right? And so there's a lot of just these differences among models. So long story short, if you use these models well, if you compose calls to these weaker models in an intelligent way, like a verifier-prover structure on R1, even if that is 5 calls, you'd still be 1/1000th the cost of O1 Pro. And so one of the best examples of work illustrating that is actually work by Alex Demakis here at Berkeley, who was a faculty in Skylab and EECS. And Alex basically created this super simple regime that he calls iconic decoding, where he'd basically take 5 R1 calls. Academics like R1 because it's open source, right? He'd take 5 R1 calls, and he would basically notice this quirk of R1, where, long story short, when it's stuck, it's very, very hard working. So it'll keep trying. More thinking time is basically more effort. And it's kind of like searching. It's like a tree search over like different approach paths. And if it gets stuck, it'll backtrack. And so basically what he found was that the longer the thinking traces were, the more likely it is to get the answer wrong because it went down a wrong path initially and wasn't able to backtrack before it ran out of time. And so roughly speaking, he found that if you ask the same question to 5 replicas of R1, and you pick the shortest answer, that shortest answer had a much higher probability of being correct than the longer answers. Just an interesting quirk of that model. And so using that quirk, he said, okay, I'll just create a simple algorithm of early stopping and selecting the shortest answer. So basically you run 5 replicas, DeepSeek wraps its thinking in these kind of thinking tokens. So you wait for the first thinking token, then you stop all the replicas and return that answer. They got the thinking token. And that simple protocol is faster on average than a single replica. It is smarter on average than a single replica, but ironically can actually be cheaper on average than a single replica. Wait, how is that? You're creating 5 replicas. How would that be? Well, it turns out when the model gets stuck, it might generate a ton of tokens. And output tokens are more expensive than input tokens, by the way. It might keep going, and you're paying per token. So if you stop the ones that are going down the wrong path, you can actually, in expectation, even over 5 replicas, save money. And that's like a super simple example of creating 5 clones and kind of grabbing the fastest one. But that kind of gives you some intuition for, oh wow, like if even that simple thing helps, what types of more rich things could we do? What other gems lie in this architectural space? Right? That gives you some intuition. Great question. Yeah. Any other questions? Yeah.
Yeah, I was just going to kind of expand on what we were just talking about.
Yeah.
Is there good research on how to synthesize something out of the output of a bunch of these that is greater than any single model's output, and like what does that look like?
Yeah. Yeah, there's a few works. I referenced some of these. Maybe, yeah, I'll go on this slide. Yeah, I referenced some of them. Maybe I'll note some of these. Yeah. 2 of them that I'll note is one is this ensemble space work. It's actually a really simple idea, but there's some richness to actually being able to use it. But long story short, simple idea. It turns out that if you build kind of a group of these models, a committee of models, that committee is very good at getting a better answer to easy questions. So it's kind of funny. If it's a question where the base model by itself would most of the time get the answer right, but every once in a while it might hallucinate, putting a committee is kind of a variance reduction mechanism. It'll kind of squash the probability of hallucination. Right? Ironically, though, so that means it helps a lot for easy questions. And you kind of see this monotonic improvement on easy questions. Ironically, though, for hard questions where a model by itself would get the answer wrong, doing consensus in committee makes the probability that you'd kind of get that spark of insight to get the answer right very, very unlikely.
Yeah, it's like regression to the mean, where the mean is useful in simple questions and bad in complex.
Exactly right. A variance reduction, regression to the mean. And so in those cases, having more calls, which by the way, intuitively, that's when you probably would have even wanted to use this type of approach. Like you'd probably want to use the approach of making multiple calls for hard questions, intuitively. Turns out it makes everything worse. So not only did you spend 100x, 1,000x more money, but your answer is actually worse. And so you're pretty unhappy in that case. And so you kind of need to be able to discriminate between easy and hard questions to apply the scheme appropriately. Right? And so that's kind of one small example of some of the types of things that have been done. But yeah, it helps. If you're able to do that well, then you can kind of use this idea to almost route. But instead of routing amongst models, you're routing against these kind of architectures.
Yeah, it's like a different kind of semantic routing.
It's a different type of semantic routing. Same thing with the best of n graphs. The best of n graphs actually turns out is a really simple primitive. It's almost never worse. In none of our experiments was it worse. It's kind of like O1, where you might have seen, if you recall from the early O1 model card, O1 was not better at some things. Like if it was creative writing, they said it wasn't helpful. But it was helpful on math and code. Same with some of these architectures. Like they're better at some things, but they're never really worse. And so that's something that just in general, I think if there's like one thing that people should try, it's if you have a sticky task, the simplest thing you should try first is just creating a little graph with 5 models. Same model, different models, doesn't really matter. 5 of the models that you think would be good. Having those all generate their own base answers, just giving them the question, having them generate answers. And then having a simple judge, where the judge prompt is basically, here's 5 different perspectives from your advisors. Considering this perspective in the original question, answer the question. In the most simple case, just like a synthesis judge. You can also just select or whatever, but just the most simple case is just that. Just like give all the answers to a judge and tell it to give you a final answer.
So it actually synthesizes across the answers.
It can do that too. Yeah, it can do that too. Yeah, that simple thing will probably help in a lot of your contexts. Yeah.
Is there a suitable number of how many instances are optimal for?
Yeah, the question is there a number of how many instances are optimal? No, partly because of the dynamics I just mentioned, where there's more richness to this than you think. It depends on your question, depends on whether it's easy or hard, depends on a number of things. I'd say probably as like a simple thing, I recommend just like something reasonable like 5. It's just to almost just kind of be really prescriptive. I think 5 calls, just try that. And if that helps a little bit, then you can try to push it further, right? All these things, like the reason this is so rich is it's a function of your specific setting and your SLOs and SLAs, right? So for example, if you have a task where, like, I'll give Harvey as an example. Harvey's a legal AI company. The briefs that they generate with LLMs are really, really valuable. They're not that many words, but like people pay a lot of money for these reports. And a good report is worth a lot of money. 1 million tokens sounds like a lot, but 1 million tokens is like 5 books. It's a lot. Like $150 per million tokens is actually not that expensive if you think of it that way. And so if I only want 1,000 tokens in like a report, I'm willing to pay $1,000 for a good report. I want to give you more money. It's like, please, OpenAI, take my money. Like, I'll pay you more for a better answer. Is how, if better, yeah, exactly. So that's kind of how people think about this, right? And so what I think part of what we're trying to do as a research community overall is find methods that can better assimilate money, or compute rather, and turn it into good answers, right? To kind of have some scaling curve like that. That's exciting when you find those, right? And, so depending on your problem, you might find that 1 call is enough, 3 calls is enough, but maybe you keep getting improvement in your task as you add calls. So it depends on your setting. Yeah, please.
On the same topic, but this kind of reminds me of the secretary problem. Right?
Yeah.
And so it's like, too many people do some sort of cook until done thing, where it's like,
Yeah.
we're just going to do X of these, give the judge that context,
Yeah.
this has happened, and then find the next good answer that comes out of it.
Yeah.
Is that relatively successful in a broad range of questions?
Relatively successful in a broad range of questions. In fact, actually, the network of networks paper that is kind of mentioned here implicitly in that best of n graph context, and I showed it on a prior slide, that paper looked at these judge-based systems and kind of a cryptographic way of analyzing them. Long story short, as long as you have a judge that has, I would say, is more likely to certify a correct answer than it is to certify a wrong answer. That's it. It's picky. It's not perfect. As long as it has a better than random chance likelihood of saying a correct answer is correct versus a wrong answer is correct. That is the only criterion necessary to be able to kind of put, to get improvement as you increase K, aka the number of ensemble members. So it's pretty simple. That's really it.
That's fantastic, honestly.
That's really the only principle. If that principle is just satisfied, then you can put more and more compute into this type of.
Then you can go back to the
Here's more money, you get a better answer. Now, the rate at which you get a better answer might not be satisfactory. But you want to push that. All right. Exactly. At some point, your boss, is going to come in and say, does this make sense? But yeah, I think, the takeaway thing, so if people want to follow this line of work, feel free, as I said, to reach out to me. If you're doing work on things and want to, talk about it, love to talk about it. Here's my personal email. Also, you can follow pyember/ember on GitHub. We're going to be pushing some great updates. We already have some great code there, but we'll push some new kind of improved version of that framework, along with a lot of research from different collaborators in the coming couple weeks. Yeah, so look forward to talking more. Thanks for your attention.
Our next session will be focused on the multimodality challenges, neural operating system, and deploying AI agents by Lambda. So we will hear insights from Amir Zadel, who is a staff machine learning researcher from Lambda. So let's get started. Let's first welcome our speaker.
Thank you for the introduction. And just for you all, my name is Anthony. I'm a technical product marketing manager at Lambda, and today is designated MC. And so just as our host here noted our agenda items, these are a few of the things that we're going to go through this hour during our workshop. And I'd like to introduce my colleague, Danny Kraus, who will be presenting to you Neural OS, our neural operating system.
I wanted to provide a little background about how I think about agentic AI, sort of in terms of this project, because it can mean a lot of different things to a lot of different people. So Nolan Bushnell had this famous quote, and I literally can't see it, so I'm going to have to paraphrase. But it's basically, everybody who's ever had a hot shower has had a good idea, but it's the people who get out of the shower, dry off, and then go do something that make an impact. And that do something part is where I think the agentic AIs can really shine, right? Like, you can have more and more complicated layers of something that takes text that a human gave it and spits out a better answer, but that doesn't do anything. That's just text coming back. So you got to wrap it in something that can do something and then hopefully get that feedback loop. And so we made this kind of crazy idea. Our CEO started working on it, and we kind of took it over. And he basically said, like, hey, like, a computer, is a series of programs. Talented people program it. Hopefully, it's bug-free, of course, never a problem. But when there is a problem, then you got to release updates, and then you got to have more people working on it again. And you're sort of like, okay, imagine a world in which the LLMs were good enough that they could be the computer itself, right? You could give it a complex enough prompt that says, like, hey, you are a computer. You're going to accept these inputs from the user, and you're going to do whatever it is that they want. And then you're going to pretend that you're a computer and keep going. And so we whipped together this demo that basically it's wrapped around just like HTML and CSS right now. So you give it a prompt. It took us a while to craft the prompt that was able to like do these sorts of things. But I originally was just going to ad-lib this with no visuals, and this morning I was sort of like, I don't know, let me get Neural OS to make a slide. So I literally asked it, like, hey, I didn't tell it the quote. I said, hey, do the Bushnell quote about the shower and generate an icon that's relevant. Unfortunately, the first time I did this, it generated a better icon, and I lost it. But this is the second time that I did it. I still think it's doing pretty good. And so the idea behind it is that you can have this interaction with it, and it not only gives you the sort of visual possibility of whatever's coming back, but it can also network to other ones. That was the other thing that we wanted to do. So we have a relay server on the back end that connects them over their IDs, and so you can actually have these things talk to each other, which, sorry, again, I didn't plan on doing this exactly this way. Nope, wrong way. Okay, so here's an example of a random thing that I did this morning where I was like, hey, establish a chat with this other instance. So you are seeing one instance of it, and there's another one that I have over, there's an incognito here, an incognito window that's the other instance that sent the messages. So I asked it to establish like a synchronous chat application with, and you give it the ID of the other one, and then it would synchronize them and actually put them together, which I think it did a pretty good job. And I wanted to also sort of demonstrate that it can actually like go out to the web and do things. So I said, hey, tag each text thing with an image that's relevant to whatever's being talked about. Again, traffic was bad, Golden Gate Bridge with a bunch of cars, and it's like, hey, I should take my bike next time, and it's just a picture of a person with a bike in a field, which is not bad for its first try. And I can't see too well, but we've had a lot of fun doing these things. We initially had a bunch of questions about like, what's the security model look like when you're like having an LLM interact with another LLM that's not yours? And we decided to just blow open all the gates and have no security. So you can, if you get somebody else's ID, you can have it, pop up annoying sounds. One of my coworkers did that to me. It just like opened up in my web browser without my knowledge. But the idea is that you can sort of wrap your mind around how you would have instructions to an LLM that would be able to generate these things. And then you can get into the sweet spot of people who are not necessarily super technically minded, but want to make something. And they could figure out how they want to make something. And then you get into this really interesting part of, well, it doesn't quite work right now, but if I shelve this for, honestly, a frighteningly short amount of time until somebody comes up with a better LLM, and then I just put this exact same thing back into it, I can effectively get better outputs with the same sort of source code. That's the LLM that you first, or the prompt that you fed into the LLM. So then like the prompt basically becomes the source code. And we added some glue here. There's a bunch of things that it can do. You can actually, you can ask it what to do, what it can do. So we gave it some ability to go to the web and like get things, which has been fun, definitely. But I think that one of the things that's most interesting about this is that everybody's experience, even my own experience, is different because there's an LLM that rendered this whole operating system each time. So when I log in, like sometimes there'll be icons on the left, sometimes there won't be, sometimes they'll be in color, sometimes they won't be. And different neural OSs, when they get these messages across the network, then that is run through inference again, right? And so sometimes this synchronization between things works, sometimes it doesn't. I like lucked out that the first time that I did this for this demo it worked. I thought I was gonna have to capture some screenshots for it, but we're really hopeful that you can play around with it and figure out if there's something there. And we're gonna work on extending the things that it can do and giving it more agency and putting my computer to sleep. And yeah, that's basically how NeuralOS works. You can go to neuralos.com and try it out. It's open to everybody. Yeah, that's it. Thanks so much.
And that's not all we have to show. Here in the next segment of our presentation, we'll be doing a demonstration of how you could deploy AI agents using our managed serverless inference API. So that's the presentation I will be giving right now. But before we get there, I'd like to set the stage a little bit. So let's run a hypothetical scenario, and let's all pretend for a moment that we work for an organization called Space Outfitters. And just imagine Space Outfitters to be just what it sounds like, a shop where we could outfit you with all your needs for your space travels. And so in this hypothetical example, let's just put ourselves in the role of an employee there that might be wanting to deploy AI agents to automate some of their executive reporting. So in this case, in this example that we're going to show, we have created 3 different agents, one that reports on both consumer sales, another that reports on B2B, like distribution sales. The second would be summarizing campaign impact and growth metrics for our marketing operations agent. And the third will be one for customer supports, one that summarizes issues and satisfaction insights. And then wrapping this up with a presentation to the board. So before we show you how to deploy these agents, I just want to give you like contextual understanding of the workflows if you're not already familiar with that. So what is an agent? An agent is simply an automation workflow that is prompted with a role. It's granted a title, in this case, sales reporting agent, and it comes equipped with a goal and a backstory. These are all codified in YAML files that are accessible in our GitHub repo, which we'll display here in a moment. And these agents are pretty purposeless if they're void of tasks that include descriptions, expected output, and are attributed to said agent, as can be seen here in this YAML file related to the tasks. And lastly, these agents are incomplete without their tool. So in this case, it's a Llama index CSV reader with the following code can be seen here. Now, how are we structuring these agents? So like I mentioned, the first sales ops agent is one that's summarizing reports for both consumer and commercial sales. And this singular marketing ops agent is doing the same thing and consolidating the insights for consumer and commercial sales into a singular report. But as you could see, the customer support operations agent has a little bit more of a streamlined workflow. But we just wanted to share this as like a visual representation of how this deployment kind of works under the hood. And as you could see, this is just a visual of that workflow at a more granular, data-driven level. But this state of the business report here is essentially the format for the reports that this agent will render. So it includes an executive summary, key metrics, as well as month-over-month performance comparison. So this is the anticipated output of the agents that we will be deploying today. Now, how these get deployed, like I mentioned, we have a repository available on the Lambda GitHub titled AI Agent Masterclass. Now, no need to feel the pressure of following along with this exercise. I could give you all details to kind of replicate this at home, and I'll be providing you instructions as to how you could do that along the way, and we could save questions for the end. But very simply put, it's just as easy as we'll be demonstrating for you today. So it starts with ensuring that you have all the proper requirements. So in this case, ensuring that your Python is up to date, that you've downloaded the OpenAI Python library with this command, pip install. Ensure that you have a Lambda Cloud account with an API key created. And the important step here is to ensure that Docker is actively running on your desktop. Simple enough. So in these short few steps, we'll show you how to run an Agentic AI example of your own. So in this case, you would be opening your terminal, cloning the repo, and then checking out the correct branch. So you just git clone the URL for the repo, and then cd to the path where that repo is saved locally. From that point forward, you will be creating and saving an .env file that includes your Lambda API endpoint key, and you could feel free to choose your preferred model. So selfish plugin here. We recently launched an inference API about 6 months ago. We host up to 19 different open source and proprietary models. So you could swap out any of your choice here. We include Llama 4 Maverick because it is capable of some multimodal use cases. All right, and in this example, we're just showing you how to test that API. So you just enter the command source.env, and you submit a curl command to the API key, and it will generate text like so. And this just shows you the availability of the different models that we offer here. Great, and the last and final step is building your crew of agents. So this was built using Crew AI. They happen to be a partner of ours that we work closely with sometimes. But in this case, all that's required is building the Docker image, running the container, which copies the reports. So once again, just copy this command and drop it from our repo and drop it in your terminal. So what does that look like exactly? Really quick, I am going to navigate to my desktop, which is usually crowded with tabs. But here in this case, I just wanted to walk you guys through really what that looks like. And don't be alarmed, this produces a great many number of tokens. But as you could see here, I followed the examples that I walked each of you through. Here in this case, I had the repo saved already. So I just CD'd into the folder. I tested the API in this case, and then I entered the the build Docker image and run container command here. And so what that does is it reviews all of these the metadata in each of those files. And as you can see, it's formatting the output in just the way that we've requested, and is analyzing each of these reports. These reports are generated using synthetic data, so no privacy concerns here. And just as an example, this green text are like the token output. So as you can see, it's given the task. And here is the synthetic data from those reports that it's analyzing. And these are the system instructions. Now the output of that can all be seen here. I just want to scroll to an example. Like I said, it produces many number of tokens. And as you can see, here are some of those reports. This is specifically on the B2B sales reporting. As you can see, it generates an executive report informing you that close one revenue is up by, or decreased 15% since February of 2025. So this is just high-level overview, but as you can see, pretty plain and simple. Given your data sources, this repo, and our inference API. So just a quick example of how multi-agent workflows can be deployed in the workplace. And this is just the second segment of our presentation. I would like to introduce our colleague Amir, who will be sharing more details about our research and multimodal challenges and tools. Thank you.
Thanks for the introduction. I'm Amir Zadeh. I'm a staff scientist on multimodal learning at Lambda. We have had a lot of progress, obviously, in AI within the last 2-3 years. The main reasons, we had compute, a lot more compute, and a lot more data, right? And now we have all these nice foundation models and all of the good things that they can do, such as agents. But the outlook for multimodal learning, where we have all these different kinds of data that can come from different sources, and some of them may not actually be in the petabyte scales that we would want them to be. Text is easy, images somewhere in the middle. Video, now we're kind of threading on these dangerous gray areas. Do we have enough videos or not? Then we go into MRI, CT scans, infrared, all of these modalities that we just don't have enough data, right? So there is also another piece of bad news, is that even in those areas that we do have enough data, we're going to run out of new data points by 2028. So that's the projection that we have. So we need to start thinking about, okay, compute seems to be the area that we can push further, unless we get everybody on the planet to start annotating. But that's not going to scale either, because if we double the size of this, the training will probably take another extra day or two. So this is going to be a problem, ultimately. So today, if you look at what we have in the field, primarily we have two camps of foundation models. One is camp diffusion, and one is camp autoregressive, right? And they are being studied on different areas, meaning that vision people are now trying to do autoregressive, diffusion folks are trying to do text, and so it's not quite clear which one of these camps is going to be the ultimate winner in this situation where we're going to run out of data but not out of compute. So this paper talks about It's a collaboration between Lambda and Carnegie Mellon, where it basically says diffusion will ultimately beat autoregressive in data constrained settings. It's just a matter of compute, and diffusion will do better. So I also want to introduce quickly the co-authors. Mihir and Mengning are both students at Carnegie Mellon. Katerina and Deepak are professors there. I also got my PhD from CMU. So let's talk about diffusion training. Diffusion training, you basically create these masks, and at least in the discrete diffusion, you create these masks, you try to figure out what those masks should have been, and you get rewarded for predicting them correctly, or you get penalized if you don't predict them correctly. Autoregressive is also a case where we basically try to always predict the next token within a sequence, and sort of like go from I have 3 masks, then 2 masks, then 1 mask. So we want to do this study where there is this notion in large language models that you need to train for 1 epoch only, right? There's no need for extra epochs. And part of the reason why diffusion folks have fallen behind is that we stuck to that belief that 1 epoch is always going to be the same, right? That's true for a case of autoregressive, meaning that let's say if I have 100 million tokens, right? At some level of compute, the tokens are no longer making any difference. My loss is not going down. And the flops that I throw out at this, even if I go in the scale of exponents, is not going to help me as much. But on those same 100 million tokens, if I just let diffusion train for more epochs, and this is on more epochs set up as well. So both of these are being fairly compared together. Diffusion will ultimately beat autoregressive. What's even more interesting is that there's this moment of critical compute point, meaning that there is a critical compute point where we can also identify exactly where that point is with certain approximations. If you tell us, for example, what number of tokens you have and how much flops you have, you'll be able to predict this critical compute point, and if your budget allows to go beyond this critical compute point, you can throw more GPUs into the pipeline and get better. We also do this for 50 million, and another interesting trend shows up is that diffusion is also more data efficient, meaning that ultimately autoregressive is incredibly data hungry, but diffusion can use lower amount of data in order to do better. So there is a way to compensate for the flops issue that we had earlier. So the check of these Pareto optimal and critical compute points is interesting. We want to sort of like get a little bit deeper into this. There's really one thing we need to be concerned about. There are some ways in machine learning to calculate scaling laws. In the paper, we introduce an extension of those that applies to both autoregressive and diffusion. Autoregressive has been studied a lot. Diffusion has not been that much. So we sort of like unify the framework to study both autoregressive and diffusion. But one of the interesting things that comes to mind is the half-life of data. Just like nuclear sciences, half-life basically means at what point can you expect this whatever it is to die within the next however much it was before that, right? So if I had half-life as t, it means that ultimately this particle will die within the next t. Half-life of data means that at what point is this data less than 50% useful for us, meaning that the information that this data could give us, it has given us. And this is the stark difference between autoregressive and diffusion, where after 31 epochs on the 100 million tokens, you are basically done. Half-life has reached. Autoregressive can no longer extract more information from this. But the half-life of the same data in diffusion occurs in 493. meaning that after 493 epochs, you still have 50% more to extract from that data point. So this is something that's interesting. Why is this particularly interesting in multimodality is that exactly we talked about how data is eventually going to run out and we need more scalable algorithms as opposed to being bottlenecked by both data and the algorithm. So now there's also another interesting thing. We talked about the half-life, but what about being almost new data, right? Meaning that at what point in training, like let's say if I have an autoregressive foundation model and a diffusion foundation model, at what point can I expect this the new data points that are happening within the same epoch over and over again to no longer be considered new data points? This happens based off of the tokens. We have drawn this based off of token and the validation loss. So almost after 4 epochs, the data is no longer new for the autoregressive, meaning that the autoregressive has exhausted that data point. It can no longer extract more out of that. It can no longer, you can no longer consider it as something that's going to surprise the model. But for diffusion, that happens after 100, right? So this means that despite the fact that both of these algorithms are working on the same type of data, diffusion treats data points with more, like extracts more information out of these data points. So now there is an interesting moment where we can say, okay, like all of this is great. What should I do? When should I use diffusion over autoregressive, right? The formula is relatively simple. I mean, there's a lot of like evaluations, like thousands of experiments that we had to do, and all of these numbers are empirical. But you technically have 2 things. One is the number of tokens, unique data tokens that you have, which is U, and then flops. So you can put in U, solve for flops. You can put in flops, solve for U, figure out at what point roughly diffusion will start beating autoregressive in in the training that you have based off of the tokens. So this is interesting because a lot of people don't necessarily know what to do if they're in a particular field. They're like, oh, do I choose autoregressive diffusion? If you're like the message is very clear. If you're compute bottlenecked, go with autoregressive. You're going to be able to get to losses, good losses faster, right? If you're data bottlenecked, go with diffusion because you have more flops. You can go down that line and really optimize your model. And for example, in one of the cases like in robotics, where you have simulations, go with autoregressive, right? If you're doing real world training, do with diffusion, right? So we hope that this paper will kind of like shed light on making it a little bit more of a selective choice and something that folks are informed about it, as opposed to like, I'm gonna try diffusion and autoregressive, both of them, figure out what happens, right? Because that is probably a recipe for disaster. Both of these models are incredibly expensive to train at the end of the day. So this way, at least we can save half of that money. So yeah, thanks for this. So I don't know what happens next,
yes.
Anthony?
I'm here for that. So
Okay, great.
We will now open the floor to any questions.
Oh, questions. Do I have to be as well?
If there are questions about the research.
Okay.
Any questions for the research presentation that we just had?
So from a cost perspective, AI versus diffusion, which one do you recommend? Let's say if money is not a problem, data is not a problem.
Money is not a problem.
It's always a problem.
Data
Is a problem.
I think you can just train a fully connected neural network if you have that
which one
ever.
is expensive to run?
Well,
Go to the microphone, you answer.
oh yeah, sorry. Yeah, so I think That's kind of a very utopian world there, but if I'm looking at the current state of real world, by 2028, we know for a fact that we're going to run out of, unique data points, right? Where something is going to really shock us, like if we see it again. So my suggestion based off of this is that models that are inspired by diffusion or are under diffusion family have a higher chance, because we know that there's always going to be compute. We can always grab more silicon and just start building these chips. But data, we're running out of the fossil fuel of data, which is internet. So yeah, that's the unfortunate reality today.
The specific year, like what's the rationale behind saying that back this year we have no new data, and isn't data just increasing day by day?
Not as fast as, yeah. So the question was, if I understood it correctly, isn't data just increasing on the internet? So wouldn't that make sense to just use autoregressive, I suppose, right? Yes, the answer is both data and compute are increasing, but compute is increasing much faster than data is right now. Especially if you think about it, now that we have LLMs, a lot of generations are going to be based off of the LLMs. So really new data points generated by humans and by professional humans, I suppose, is going to be very limited. Yep, so that's the problem that we face. Any more? Okay.
Why is diffusion better at extracting intelligence from data? Is it just because it can pay attention to more of it in any given training moment, or?
That is a very good question. Here we didn't answer that one. The only thing that we know is that it is not because of better augmentation, meaning that there's definitely things to be studied underneath and figure out, okay, like what is really happening. Because we did experiments on augmenting the data for autoregressive the same way as we did for fusion. It works the same. So. Yep, okay, thanks.
More? Thank you. Do we have any other questions in the audience from the first or the second segment of our presentation on neural operating systems and deployment of AI agents? No? Well, we must have done a good job then. Excellent. Well, thank you for your time.
So now we are at the second and last session, which is focusing on the vibe coding with Goose, building apps with AI agents and MCP by block, which will be presented by Angie Jones, who is the global head of developer relation in the block company. Yeah. So now let's welcome our speaker and let's get started.
Hello, everyone. Thank you so much for coming today. My name is Angie Jones, and yes, I work at Block on this fantastic open source agent called Goose. Got a little echo? Oh, okay. Yeah, so Goose is an open source AI agent. It's built as an MCP client. How many people are familiar with MCP? Okay. And so MCP is an open standard that essentially allows agents to connect to tools to be able to actually do stuff versus just kind of telling you how to do stuff. So in this workshop, it's designed to be interactive where you vibe code yourself. However, if you would prefer not to, that's totally okay as well. You can just kind of sit and watch and we'll kind of go through the stuff. So you pick your own adventure if you want to vibe code or if you just kind of want to hang out, all right? Cool? All right. Y'all have to liven up for me though. All right? Okay, so here is the URL. Does everyone have it? You're going to need this URL. So this is your, and for those online, it's Agents-Workshop. And this will be your companion for today. So everything that you need is in that guide, okay? All right, we ready? Okay. So I'm going to go over to the guide. And we're just going to work from this guide, okay? So let me make it bigger. All right. So first of all, the objective today. So what we're going to do is vibe code to create a new product, right? And this product is going to be called AI Brief Me. So the way it works is we'll have an app that you can basically put any topic into and then say, hey, just brief me on this topic. And it'll give you a couple of summary bullet points, maybe a graph, maybe a code snippet, depending on the topic. So we're using AI to build it, and it'll also have AI embedded in the product itself to have, you know, some features there as well, okay? So what we're gonna do is use Goose to spin up a team of agents that are gonna work on this together. So Goose has a lot of functionality in it. It's very similar to a lot of the agents out there, but it goes a lot further as well. So yes, it can vibe code, but it also can do things like orchestrate multiple agents. It's also LLM agnostic, so you can bring whatever models you want. And I'll show you, hopefully some of you have already done this, but I'll show you where you can basically get an API key. So your vibing is on me today, okay? And then whatever you have left, take that key home. You can continue vibe coding, build your next app. Remember me when you're famous though, all right? Okay, so for this app, we're gonna do 7 sub-agents. We're going to do a planner who's going to define what the product is and what an MVP looks like. What's the scope of this, right? We're going to tell it, look, we only got like an hour, so don't go crazy. This is not an 8-week sprint. This is what can we do in an hour. We'll have a project manager that's going to coordinate the task, kind of break it down, what needs to be done and who should be doing it. We'll have an architect that'll like set up how this should be designed. And then we'll have our front end and our back end devs that will work in parallel to build the app. And then we'll have a QA come through after it's all built, write some unit tests and tell us what's wrong with it. Heads up, something will be wrong with it, right? Because we're vibe coding. Y'all, don't take your vibe coded app to production. Did you see the, what's the name of the app? T something something? What's it called? T. Yeah, #1 app. Riding on the clouds until you're not, right? And so we'll have a QA that actually lets us know, is this production ready? Probably not, but it'll let us know what we need to do to get there. And then we'll also have a tech writer to document some stuff as well. Sound good? All right, so what Goose is gonna do is orchestrate all of this. Today, we're gonna use Goose as sub-agents as well, but Goose is highly flexible. Block is the company that created Goose. Block is a fintech company, right? And so this is not our lane. We just have brilliant engineers who build stuff like this. And so we open source this for developers to enjoy, okay? Which means we can be really unopinionated about a lot of things. Bring your own LLM, right? You want to use Claude CLI or Gemini CLI as a sub-agent? Sure, why not? We allow all of that in this framework, okay? So it's really powerful and extendable. Okay, so each of those roles will be powered by a sub-agent, and what you're gonna do is kind of write the prompts that tell that agent what its responsibility is and what it should do, okay? But little heads up, I'm gonna skip down to the task section. So when you write this stuff, for each one of these, I've written out what the task is. You can prompt this yourself, but I also have a little cheat sheet, so if you're getting stuck or you feel like, I don't know, I'm missing something here, then you can just take a little peek at the cheat sheet and there's a prompt for you there. So if you just want to copy all the prompts, that's cool too. We'll never know, okay? All right, so to install and configure, how many people have not already installed but you want to? Okay, so we'll give a little time for this. So under the install and configure, you're going to install Goose. Goose does run locally. So it's a local agent. It's not hooked up to the cloud. Again, you bring whatever LLM you want. So some people who like to go totally local use things like Olama, and now you have a full offline experience. You can code on the plane, on the train, or whatever. But if you want a more high performant model, you can use all of them. You can use Claude models, you can use OpenAI models, you can use Gemini, whatever you want, you do that. Today, the API key that I'm gifting you is with Open Router, meaning there's a large selection of models you can choose from. So choose whatever you want, but I do recommend Claude Sonnet 4 because it was born to code, okay? So if you go to this link, and then go under the install and configure number 2, where it says get the LLM API key. Just click that link and it'll let you put in your email address. When you get that, go ahead and download it, okay? Don't just copy and paste it because you won't spend all the money that I put on there for you. That means I want you to take it home and continue coding on me. When you make your app, think, Angie, wow. That girl is something else. Okay, for those of you who have already installed and configured, there's also another step. So the sub-agents feature, we rolled this out pretty recently within the last couple of weeks. So it's still considered experimental, right? And so you're going to need to turn on that feature flag to enable this. And you can do that right inside of Goose if you want to, or you can do it manually. I've put the file name there if you want to just add it there yourself, but you can just tell Goose to append that line to your config file. So look at Goose, already working for you. Yes?
I have a question. How do you define sub-agents?
Oh, good question. How do you define sub-agents? Okay, so Goose itself is an agent, right? We all know what agents are, yes? All right. So a sub-agent would be an agent that's basically spinning off or talking to another agent, like controlling them, if you will. So there's like multi-agent where maybe you don't control that agent, but you need to communicate. Like say you had an agent and I had an agent and they just needed to communicate so that they could do something for us. That's one thing, but a sub-agent is where the main agent spins off these other agents to do a task. So it's orchestrating everything. It says, look, I have this big project to do. I'm going to make an agent that does this, one that does that, one that does that.
So are these predefined or agents get created dynamically?
They're getting created dynamically. We're going to create them on the fly. Now, we do have a feature, since you asked, we have a feature that's called recipes, and recipes are a way to basically repeat something or share something. So if there was an agent that you wanted to keep, say for example, like I need a math tutor agent, right? You can make that into a recipe and it persists. That way that you can use that same agent later if you wanted to. But the ones we're doing today, they're getting spun up and then they're getting spun down. We'll never hear from them again. Any other questions? Okay, how are we? Did we install Goose? Anybody didn't yet? Still trying? Okay. Got your API key? All right. And did you turn your alpha features on? Anybody did not? Sometimes that happens. Close Goose, reopen it, and redo the thing. I'm not sure why that happens, but I have seen that before. Everybody good? Everybody have the alpha feature on? All right. You all are doing amazing. So we have about 50 minutes to whip up this project. Do you also have Node installed? Anybody don't? Or you don't know if you do or don't? Okay. So the way you check is by node -- version. If you get a version back, you know you have it installed. If you don't get a version back, then you'll need to go to Node.js and install Node. The reason we need Node is for our project, so we're actually going to kind of run a local server for our project, okay? Also, you'll need it for one of the optional MCP servers. So I want to show you a little bit in Goose. Let's do the workspace setup. So the first thing that I recommend, listen to me, make another folder. You don't want Goose just throwing folders in your other folder, right? So make a new directory, and this will be Goose's playground, okay? So the way that you do that is at the bottom here. Let me make this bigger. So at the bottom here, I have this little folder icon. You click that and you can direct it to whatever folder you want. I again recommend you make a new one and then do this step, okay? I'm gonna actually, all right. The other thing is the mode. So agents work in various modes. There's autonomous, which means have at it. Do whatever you want. Don't ask me for permission. Go wild. I like that mode. All right. There's also manual mode. That means before you take any actions, you must ask me first. Okay. So if you look, Goose, I don't know you like that. Let's see. You can go in like a manual mode, but it's going to be slower, right? Because you have to approve everything. And then there's smart mode, where it says you can read all you want, but if you do anything that's edit, whether that be write, delete, anything like that, then ask me, okay? And then chat is when you just want to have a conversation. You're not looking to take any actions. Maybe it's just a brainstorming session or something like that, all right? We're good? Okay, the other thing is extensions. So extensions, in Goose ecosystem, we call extensions, but they're basically just MCP servers. So you can connect any MCP server you want to Goose. There's over 5,000 of them out there. This gives Goose additional capabilities. For example, I have a bunch of stuff, Airtable, Asana, I have Blender if I want to do 3D modeling, I have Canva if I want to make pictures. I have all sorts of things, the Google Workspace, so it can do things on my calendar. You can make this agent into whatever you want. For this workshop, there's one that we definitely need. It's default, it's already built in, it's called the developer. The developer MCP server can do things like run commands, it can code, it can create files, and that sort of thing. Computer controller is a nice one. This one can open browsers and take screenshots. You might not need that one for this one, but I just keep it on. And then the other one I would recommend, and I have a link to it in that doc, is the Goose Docs. So as you're working and you're prompting and maybe something is not working and you want to ask Goose, hey Goose, how do you do such and such? It can basically look at its own docs and reflect on its own behavior. So then it knows, okay, this is how I need to make a certain call, or this is how sub-agents work, or whatever. So it will be able to answer your questions, all right? Okay. So let's go back to our first task. And where's my browser? All right. What we want to do is start on the first task. So our first one is the planner. So you're going to have the planner define the product vision in the scope. And the planner should decide what the app is, what it's for, what problems it solves, and the core features of the MVP. All right? So the output should be a product definition, not code, just a file, if you will. I recommend having it write this out to a file so that other agents can read that file and they know what to do. So something like a plan.md, for example. Agents love Markdown. So anything that you write that's like textual, you should probably make it a Markdown file. So we have a plan in place. Now we want to summon up a project manager. And so this project manager is going to break down the product or the project into tasks, right? And so they should define like which roles are needed. Do we need a front end? Do we need a back end? How do we list specific tasks and then assign them to folks? And also indicate which of these tasks can be done in parallel versus which ones need to be sequential, for example, right? So you'll take a few minutes. I do recommend that you have the project manager write to a file as well. Not the same file, but maybe like projectplan.md or something like that, okay? All right. And you can do this either in the same session that you're already in. You can actually continue the conversation. That way Goose has context. If you were to make a new session, Goose would not have context, but you have that plan document that the planner made. So you can say, hey, just go look at that plan and do something. But I would just do it all in one session. Exception would be when we're ready to start the server at the end. You can tell Goose to start the server, and he will start the server, but what's going to happen? He's never coming back to you, right? Because he's off in the server land somewhere, and so he didn't get it returned back to the terminal. So that's the only time I say, like, okay, Goose, you don't run those. I'll run servers, and you run everything else. Yeah. So this little icon in the upper right corner makes a new chat. So you can have two chats going at the same time. They're not chatting together, though. But funny story, the other day, I was just curious. So Goose comes as both a desktop as well as a CLI. You can use either one, and they work the same. I just had this like funny thought, like what if I had Goose desktop go talk to Goose CLI? And so I just told him, like, go have a conversation. I didn't say about what or anything. I just said, go have a conversation with Goose CLI. And it came back and it was like, oh, I had this fascinating conversation. I basically met myself. And I wrote a blog post if you're interested. Okay, so plan.md. Here's what, I don't want y'all to see everything. Here's what my plan looks like. We have some goals. We have the core MVP features. These are the must-haves. We have the technical stack. I love that it said keep it simple. So we're doing vanilla JS. I didn't specify, right? So if I wanted to, I could say, okay, I want React or whatever, but I just left it up to the agents. Backend, we got Python. I don't want this. Or similar, okay. And then it even defined the roles. Great. Very nice. Even told me what's not in scope, in case I want to come back later and keep vibing, you know? All right. Any questions so far? Did you get your next project plan? Anybody have their project plan already? All right. Anybody still working on their project plan? A few folks. Okay, so while you work, we'll just look at that one. Okay. So here is my project board. It's basically saying, okay, the architect is going to start first. I could really take this plan and say, all right, Goose, like go just execute the plan. You spin up agents however you see fit, but I need to fill time today. So we're going to take it step by step so that you all understand like what's actually happening. But I love this. It's like, yeah, make a design contract. That's great. An API contract. Even gives it time limits. Like, look, don't take more than this here. Love it. All right, how are we looking? We okay? All right, so the next agent that you're going to spin up, and this will be your last standalone agent. After that, we're going to get into where they start collaborating, they're parallel at the same time, all right? For the architect, you're going to create an architect agent. You're going to have it plan the technical setup. Again, it's not writing the code yet, but it should do something like choose the stack. This is where your architect is going to make that, that decision. And then have it also describe what's the folder structure so that the agents that come after it know where things are, and then flag anything that will need to be installed, okay? So take about 5 minutes there, and you have your cheat sheet. Any questions I can answer? Yeah.
In the extension, there are 5,000 MCP servers. Why do you have to choose any? Why can't it just depending on the need?
Ah, okay. So the question was, there's 5,000 MCP servers. Why do I have to look through them and choose, right? And so the answer to this is that we are in the very early days of MCP. And so it's kind of like the Wild Wild West is very much so community led, and everybody's just making MCP servers, and there's not a really sophisticated way to do this. However, the project is working on a registry that will be a service that agents like Goose could then call to that service and say, hey, my friend wants to make XYZ, or he wants me to like look at his email. I don't have an MCP server for email, so I can make a call to this official registry and figure out which MCP server you would need, and then install it for you, and then do your task. So that effort is being worked on. Everything is really kind of open ecosystem, which I love. So the registry is being worked on by GitHub, Post MCP, which has a standalone registry right now, and Block, my company. So they're working together to create this registry service. So hopefully that very question you asked will have a different answer in the next couple of months. Yeah. 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 So the question was, okay, we're like have a gazillion vibe coding platforms right now, right? How do I measure which one of these are better for my needs? Like, is there a benchmark test or something like that, right? There is something that's called like terminal benchmark that rates the agents, and it gives them a series of tests to do and then ranks them. Goose is pretty up there. I don't remember what number. I try not to pay that close attention to those sorts of things, but we made the list. But it still depends on your task. So like what kind of tasks are they giving it, and does that mirror the type of work that you do, right? And so for me, I actually made my own set of tests. So anytime that I want to like evaluate a model, for example, I have like 3 tests that I run to see like, does this model perform well with an agent doing these tests? And so I would recommend you, so that it's personal to you, do something like that. So if you're like, let's say you're looking at 4 or 5 different agents, right? If you have a specific task, use the same model across all, because the model really does matter. But if you use the same model across all of them for something that resembles the type of work that you do, you should be able to clearly see, okay, this one performs better. But also look at things like user experience and stuff as well. Do I enjoy working in this platform? Like if you're a CLI person, is it in that, or are you a desktop person, or whatever, you know? Also, the support for MCP is really important. So I would say like any agent that's not doing that is kind of behind. This has become the de facto standard for agent interactions. All right, yes?
Are there any suggested
Oh yeah, Quinn 3. Quinn 3 is it. So there was a video, you might can look it up when you get home on YouTube. It just came out yesterday, just a regular guy. I don't know, he might be a YouTube famous guy. I don't know all the YouTube famous people. But he made a video with Goose and Quinn 3, and he had it make this like vision motion type of app. All of the Ollama models have been disappointing with agents up until this point, and so seeing that was quite impressive. But you still may need to do some tweaks, like on the temperature of the model and stuff like that, to really get it performant. All right, any other questions? How did your architect do? Still working? As much as your computer can handle. So I had like 7 running at one time, and it was able to do all the things, but my battery, even though it was plugged in, was still going in the opposite direction. So it's about the system and how much you can actually do. All right, I think this is from my guy. I got an API spec here. Love this, gave me a base URL, told me the endpoints. Oh, I'm talking your language, Moot. All right. So it told me like how everything, how the body should go and everything. Okay, I like this a lot. All right, so let's move on to our next agent. We're gonna do some coding now. So we want a front-end developer and we want a back-end developer, and we want them to work at the same time. We can do this because our architect was wise enough to make that API contract. So that means now we can split up the work, right? We're not relying on back end to make the thing before front end can start working. So what you're gonna tell Goose, there's keywords you can use, things like parallel or simultaneously, like these words tell Goose, oh, they want 2 agents at once or 3 or whatever it is you wanna do. So you're gonna have Goose spin up 2 developer sub-agents in parallel, and you're gonna tell it to build that core app. One needs to handle an express server, or if you want something different, do you, but this is what I recommend. Also that developer should handle that back-end knowledge, and then you'll have another one that builds out the UI and then wires it to the back end, okay? Again, Goose is gonna execute both of these agents at the same time so that you speed up your development, all right? I got a cheat prompt there if you need it. Who's been using the cheat prompts? Oh, okay. They're like, we are not even ashamed. I'm not mad at that. Okay, all right, so take a couple of minutes and watch your agents work. How many of you are familiar with context windows? All right, so every model has what's called a context window, and let's go to one of my old ones. Okay, let's take this one. So if let's say that I ran out of my context window, meaning the way I like to describe this, a context window is basically like a sheet of paper that your agent works on or your model works on. So as you all are having conversations, things are being written down. When you get to the last line of that sheet, what do you need to do? Flip over to the next page to continue writing. That's how they work. When they flip over to the next page, some of the stuff that's on the old page, I don't quite remember, it's not in front of me, right? So that's context windows. So in Goose, if you reach the limit, or right before you reach the limit, it'll give you a little warning like, yo, you're about to run out of space. There's a way that you can handle it. One, if you get all the way to the max, it'll summarize your conversation for you. If not, you can always do it yourself. Even if you're not at the max, you just say, I want to take the summary because I want to go to a new chat and start over, right? And so you can press this little button. It's really small. Okay, this little button right here that says summarize conversation. You will summarize this. It'll give you like the highlights, and then you can take that over to a new session. So someone has already hit their context window. If you run into that, you know what to do now, all right? Okay. Interaction with who? You could, actually. You don't need it, but you could. Let's say, so Goose's context is only within the chat session. So if I start a new chat session, Goose has no recollection of anything we discussed in the other one. So if I want to go to a new topic and say, hey, look, now I want to talk about this, but here's the context, this would be great to get the summary and bring it over. It's not a file, it's like Markdown, but yes, that summary also becomes part of the context on your new sheet of paper. So now you've basically taken up a couple of lines of the new session. Yeah. Yeah.
How does the Goose work in the prompt?
In the what?
In the prompt field, so when you're active.
Like Goose itself, a session? Yes. Okay, so Goose is available as desktop and CLI. There's no cloud instance of it, but if you're a CLI user and you don't want the desktop, but you do want a visual, there's a CLI command that's called Goose Web. If you say Goose Web, it'll open a browser, but everything is still local. So it's just pointing to like a local session on your computer. It's not connecting to the internet. But then you can interact with an interface essentially. But you won't have all of these cute little menu items. It'll just be a chat window.
I was asking about if you have already existing a project and you want to edit it, how would be able to work on that like cloud?
Oh, yeah. Like in an IDE or something? Yeah. So there's one I can just like open Visual Studio Code, or I can open IntelliJ. And you know there's a terminal in your thing. So I would use the CLI, Goose CLI in the terminal to work with that. But there's also like extensions like JetBrains as well as VS Code. Extensions I can use to like really get into the project level of it all. I would say like I rarely use Goose in my editor, only like if I'm like stuck with debugging or something like that. I like to use Goose for other development tasks, like set up my environment, right? Like especially complex things where I need like containers and all of this stuff. Like it's really great at that. And that way I'm in my IDE. I don't want you in my IDE. We both don't need to be in my IDE, you know? Any other questions? Did your developers finish? Oh, yeah. So your developers are I meant to tell you that. Your developers are gonna take a little bit of time, but Goose did give it, or your project manager actually gave it a time limit and said, if you don't come back in such and such time, we're gonna just kill you. That didn't come out how I wanted it. But essentially, just let it cook, and then it'll stop itself if it doesn't come back. Yeah. Right. There's no plans to put Goose in the cloud. There's a MCP server for that. So let me take you here. So if you want to know like what all Goose can do, go to this MCP thing at the top. And then there's the, is it not there? Maybe it's a tutorial. Tutorials. Or maybe it's not published. All right, there's a pull request that's not merged yet, where someone is using a Jupyter Notebook MCP server with Goose. I don't know how it works, so I can't tell you like the ins and outs of it, but I know that it's possible. Yeah. Also, we use, and we're going to do that, actually your developer agents right this moment are using a headless Goose for the LLM part. So within our app, what we want to happen is a user asks a question, it pulls news, but then it also summarizes that. The summary part is coming from the LLM. And so I didn't tell you like go get an OpenAI. API key or anything like that. Instead, your developers are using headless Goose, which is the CLI version. You can pass the arguments to say, I want you to do this in quiet mode. You know, I need you to not make a session. You know, I just want you to do the work. We don't need to have a conversation about it. So people take headless Goose and they put that in like their CI/CD pipelines to do stuff like PR reviews or any other actions you might want to take in your repo. All right, how are we doing? Is your app, anybody app ready? It takes a little while. We'll let it cook. Y'all want to see mine while we wait? All right, this is mine. Okay, so mine you didn't even look at the project. I'm teasing. All right, so this is mine, and you can ask it anything. I asked it, like, can you give me the growth of MCP over the last year? And then I said, generate briefing. And it came back, it gave me a couple of bullet points, and it also gave me this nice little code example so that I can really understand how do I implement a MCP server. So that's basically the app, right? If I were to iterate on this further, I would probably have it like save my sessions so that I can come back to them later and things like that. All right? And then if I want to look at the code, so here's all my code that Goose made. I guess this is it. Oh, this is probably the website. Here's my server. Let's open this in VS Code. All right. So here's my server that it made. It's using Express. So you can like actually see the code. You can come in here. You can edit it yourself. What I like to do, especially for code that I vibe coded, is use like another AI to review the code. Like review that dude's work, and then I'll look at it. So I wanted to kind of get all of the kinks out before I, use my precious human time on it. Okay, here is the headless Goose. So this is running headless Goose, and basically these are the parameters. Also, look how it said max turn. So it's like, don't get out here and get lost. You only get one shot at this. Like, try it out, and if it doesn't work, just quit. All right. Anybody else got their app? Yes? Yes. Can I look at it? And you never know what you're going to get. Like, my app probably looks totally different than yours, right? That red dot means you're about to run out of space. That's the one I was telling you, so you might want to summarize. All right, we're ready for our last two agents to finish it off. So you have a product. Technically, this is where most of the vibe coders stop, right? But I want to show you like some good practices here. So, what we want to do is to also to test it and to write some documentation. So if we want to come back to this project, again, Goose won't have context of anything we've done. So we can say, hey, Goose, read the README so that you understand how the project works. And now I want to add a new feature. Like maybe I want to add where you persist the sessions and I come back to it. Yeah. Yeah, that's what I'm talking about right now. We're not going to do it because we don't have time, but we could, like that would be your homework assignment if you want homework. And I might do this myself. What I want when I look at that app, the conversations are not persistent. So I want them to be stored in a database so that I can come back to them later. So I would say, okay, now I want to add this feature. I can point Goose to the project file as well as this README, and it should be able to just add it, right? Even without sub-agents, okay? But your last task is you're gonna have 2 sub-agents, the tech writer, because we only got 7 minutes, so we gotta get it done. So we're gonna have them both work at the same time. The tech writer is gonna write the documentation that we'll need so that we can take this with us. And then you're gonna have a QA person write some unit tests, not a person, an agent. A QA agent write some unit tests for you, and also give you a report. That report is actually great because it's humbling, right? It says, all right, yeah, you got a working product that you vibe coded, you feel real good about it, you think you're about to ship this to the App Store, not so fast. Here are some considerations, all right? So take the next 5 minutes and get your tests and your docs written. Be sure, if you are writing your own prompt, we put this in the hints, but say it again. Tell the Goose to tell that tester not to start the server, okay? Because the tester will, this happened to me when I was like testing the workshop, the tester would never come back. And I'm like, the testers are always holding up the release. They wouldn't come back. So tell it don't start the server. And this is actually doing some great testing. Like it's actually mocking responses and things like that. Like this is pretty impressive, sweet. So if I were running a live session, which I'm not, so I don't know, maybe I can do this. Okay, yeah. So look, you can always just kind of, these are called tool calls. And the tool calls are basically the agent talking to your MCP server or talking to your file system or something like that. It's essentially make it a function call, right? And so for example, this one is just saying like run CD or something like that. But this gives you a lot of information on what's going on. So I can look at the tool details and then I can see exactly what the agent is doing. And then I can also see the output. So sometimes when it's stuck, I just kind of expand this and I say, what's it trying to do? I told you not to run the server, right? You were trying to run the server and now you got yourself stuck in La La Land somewhere. So if you want to know, look at that tool call and see if you're even getting any output. Notice here also, as I was developing mine, I was getting a 404 error. Instead of me trying to figure this out, I just tell Goose, look, and I pasted the errors that I was getting, and I said, can you figure it out? And it can go ahead and debug, it can try things, and even fix the issues for you. So it's really helpful with that sort of thing. Any questions on vibe coding, on Goose, on agents? Yes.
Is there a way to go back to your previous work, as in I worked on a project for 7 days?
Yeah. So here's my history. I'm going to show y'all all my business. Here's my history. Most of it is me working on this workshop. And I can go back to any of those. And when I go back to it, there's a share. Actually, I don't think you have this. This is internal. But there's also a resume. So you can resume an old session and pick up where you left off. And sometimes that resume might even be just to grab the summary so you can go to a new chat. So you can do that too.
Okay. No, as in like, let's say I did something, right? And then maybe my architect didn't drink coffee, right? So
Yeah.
I made a mistake.
Yeah.
Whatever you did in the last 1 hour, it's wrong.
So this is what I would do. You get really creative with this stuff, right? What I do is I have that Goose docs MCP, that's my favorite MCP when I work with Goose, because then it knows stuff about itself. So what I'll say is go find your log files. Something happened. Go look through those log files and determine where we went wrong. And it can then go and say, oh, let me look at the docs. Log files live there. AI is great at that. Let me summarize all these log files. Oh yeah, I see. The architect made this goof up. Got it. Fixing it. Yeah. Yeah.
One of the things that I've heard is like maybe a benefit to vibe coding is being able to explore optimal libraries for like a given use case. I'm curious about what your experience with that is.
I love using vibe coding for prototypes, right? Which is basically what this is. And what I found is that it helps me to not become like so committed to a solution, right? If I develop something and it takes me 3 months, you better love it. I poured my blood, sweat, and tears. But if it took me 15 minutes, I don't care if you don't like it. We say, okay, great. Yeah, this is not a good fit, or that's not the right library for the job, or whatever. Toss it out, make a new session, start over again. So I love it for that reason. We started using it a lot internally, even people who are not in engineering. And so they'll create a prototype of their ideas because that's so much faster than me writing like a strategy or a design doc, have everybody pick apart the words that I'm saying versus me just showing you. Here's a prototype. I deployed this little toy app, play with it, and then let's have a conversation. Yeah, yes. No. You would need to say the word sub-agent or something like that. Or even if you said parallel, hey, I want to run these 3 tasks in parallel, it'll know, okay, I better spin up agents. But you would have to give some sort of contextual clue that that's what you want to happen. Yeah. All right. How did you get tests? I want to look at the tests because I don't want you to leave here and think that you are off the hook. So here's the complete summary from the tester. So the tester says, okay, I'm done. It told me all of the tests that it created. And here were the test results. 20 tests passed out of 20. It took 1 minute to run the test. And it did some coverage metrics. So what does this look like? About 92% of the functions covered, 76% of the branch or whatever. You could always increase coverage if you want it. And then it broke it down on like the suite and what it tested, which is great. But more importantly, it says, okay, here are the critical issues that I identify. Security, you have a risk of command injection, right? You don't have authentication. There's no rate limit in here. Like you're using an LLM under the covers, you know? It's saying I have some memory leaks, some inefficient parsing. Like this would kill me if I put this like out in the wild. So now I have all of this information. It's saying you're not going to be able to scale it. The overall risk is high. I do not recommend that you release this to production without addressing the critical issues. So I love that it brought me back down to reality. I feel good with my prototype, but I realized that it's just that, a prototype, and that I need to do some more engineering to get this production ready. All right? So that is it. That's the workshop. Any questions I can answer for you? All right. I hope you all had a great time. If you think of anything, you can always reach out to me. I'm Angie Jones on all of the platforms. LinkedIn is probably where I am the most. But also we have a Discord server for Goose that's very lively and active. So if you want to see some of the other cool things that people are doing with Goose, I do invite you to join us there. Thank you so much.
This is our last session focusing on the AI agents that interact with the world around them by the authenticated zero or Okta. And Abhishek Hineka will present with his insights. So he is currently a product architect in the Auth0 and Okta company. And yeah, let's welcome our speaker.
How many here know what Auth0 or Okta is? And how many of that are just Okta because you see it every morning? Okay. Auth0 is a part of Okta, and it was an independent company till 2021 when Okta acquired us. We focus on developer productivity and building security tools for developers. So we build authorization products, authentication products, and the entire suite. And I've been at Auth0 for about roughly 9 years, 2 months at this point. So I've been in this industry for about 15, and that's allowed me to basically see through the first SaaS transition and now the AI agent transition. And so as we're talking to agents, we're talking about agents, we're working with companies, we have some insights in it. I would love to chat. This is a workshop, but it's also like a more open session, so I'm very open for questions because I'm sure a lot of folks here, they don't need a Auth 101 or they don't need an AI 101, but the intersection becomes extremely blurry. And I do want to thank Goose, Windsurf, Claude, and a bunch of agents that made this demo and workshop possible. So we all hear all of these hyperbolic statements like AI is going to eat SaaS, or AI is going to make this job disappear, or AI is going to make that job obsolete, right? And at a philosophical sense, we know, yes, technology moves forward, and therefore AI will change things. But then between ChatGPT going from a website that you would ask to do your homework to now writing Google Docs that you do your homework, that ChatGPT and AI is still interacting with the digital world. And so this talk is largely focusing on digital identities, digital conversations. And the other part, which I like about this slide, is how many of you and how many of us have built a very cool workshop, including my current one, and then you have to do the disclaimer. This is an amazing MCP server, but you have to go to this dashboard, click here, click here, click here, copy this environment variable, paste it here in a JSON file. And I'm sure folks are experiencing that. And so that's what we want to simplify. And we've kind of like isolated down into 4 sets of problems. And I'm going to switch a lot to my workshop between this, but I'm using my slides to just do the talk track. If we think about like how most of us work, we use Jira, we use Microsoft Stack, we use Google Stack, and now I don't want to go to Jira. I want it to tell me what I should be focused on. How many here hate Jira? The screen of it, the UX of it, right? But we all use Jira because it's the only way to work with it. Whereas with AI, instead of us having to interact with applications directly, you now can just ask ChatGPT or Gemini. And these agents can talk to each other. And so before, which was just 5 lines of very clear access control, is now a delegation between am I requesting something to be moved in Jira, or is ChatGPT requesting it? Or is it Gemini requesting it through ChatGPT on my behalf? And those are the problems that we hear a lot. And we're talking to customers, we're talking to developers, and this becomes a very common pattern for us. And a lot of this goes back to, we've completely recreated the entire stack. Before you had like a very nice agent, and I think this is so the workshop, if you want to follow along, it's very alpha. It's a much longer workshop. I've tried to squeeze it into the specific meaty guts and meaty bits for today. And what we're going to be building is we're going to start with a setup which is roughly your native app, right? You have a native app and you have a server. And I'm going to switch to Windsurf, which has the packages. So you have in there you have an API client, and you have a web server, right? This is very strong, very standard architecture. Your web client is going to call the API, and it's going to make changes for you. How many here want to follow along, and how many here want to just, because it's 4 p.m., I'm also being mindful that not everyone wants to write hundreds of lines of code. Is there a show of hands how many want to code along, and how many would prefer like a more I code and you laugh when cursor does something messy session? Oh, sorry, Windsor. Okay. Okay, I code. Cool. Oops. I should have not signed up for that one. So in this architecture, and I'm going to bounce around slides because now I have to just walk faster. This is how our works have looked since forever. You have a backend, you have a front end, you have a worker. This is no different than we do today. So in here, I have a front end application. It's called Stock. And as I was writing this workshop, I was using the term stock trade. I found out that that's a term that's a registered company. So now it's called Trade Demo Pro, which nobody should be confused at. So I sign in, and now I can see my portfolio. I can place orders. I can create a trade, like the simple stuff, right? Like I can buy like 11, and I bought another LexCorp. These are all fictional stocks. Some time ago, Gemini hallucinated and created NVIDIA stocks, and in one of the demos, it dropped NVIDIA by 10%. That was terrible. And this is a full app, right? So if you want to follow along, you can go to workshop.auth101.dev, and you can also just go follow me on Sam Shrek on GitHub. And I'm going to keep maintaining this because this is my sort of go-to kitchen sink for all auth things. So this is the app part. And in the API server, it's written in Hono. It's very basic. There is nothing here is like real data. It's written in Drizzle, and it's using the Drizzle ORM. And it has very basic routes. It has a bunch of routes for orders. It has a bunch of routes for portfolios and stocks. Very standard API server. The cool part is how that gets represented in the Auth0 side. So I'm going to go to manage.auth0.com. And I'm going to swiftly log out because for the sake of this demo, I'm going to be using 2 accounts. That's 4-factor authentication. That was not the part of the demo. It's just my VPN. And so in an Auth0 tenant, this would be represented something around like this, right? Where you have an API server. You represent it as an API. How many of you are working on MCP stack right now? Or either connecting to MCP or trying to offer MCP? Right hand for connecting to MCP, left hand for offering MCP. Oh, great. So in this section, you could also represent resource servers. And today, for the sake of this demo, it has my stock web app, and it has a bit more. So the first thing we're going to do is we're going to create a second app, which is our agent. And at the start of this demo, this agent actually has no tools, nothing, right? So I can just say, hey, are you functional? And it works. It's a Next.js start agent that I wrote in Vercel SDK. So if you're following along, I do leave out the code in .back.ts so that you can just cheat and move forward. All this code in this entire repository is Terraformed. So if we were to follow along, I would have been asking folks to sign up for an Auth0 tenant and then run Terraform because that would skip all the clicking. Or you can click. The workshop can go either way. So the first thing I'm going to do is I'm going to give it some tools. And the most basic tools that we can give it, because we already have a stock API, we can give it tools for, let's say it can search for stocks and it can get some stock prices, right? So I'm going to copy that over. And there's that. And I think I don't even need that one. I'm going to skip this part for now and just return just do this without that. And so for now, our stock agent should be able to start asking for stock price and stock info, right? So if I go back to the agent now, and I'll include the ... public stock tools, I can now ask it, hey, what's the stock price for Wayne? And behind the scenes, it's just going to make a direct call, and, well, the demo gods are not with us. Let me just check what happened there. Well, this is going to become a live debugging session in this way. So now I'm just going to add authentication to the agent and just skip the whole thing. If that doesn't work, I'm probably just, yep, there we go. So I'm sorry about like this, because if we do the step by step, it's easier, because I'm jumping way too far forward. I'm just going to go into problem space. I'm sorry about that. So effectively, what we're going to do first, what we would have done first, is we would have given it public tools. And when it's making a call to an API backend using a public tool, it does not need a credential. It does not need an access token. It does not need any sort of way to authenticate. Maybe you could give it a machine-to-machine for rate limiting, but ideally when you connect a public tool, there's no authorization or no access control required, right? And so at this point, the agent can fetch prices for you, but the agent can't actually do anything on your behalf. And that's where one of the problems that we're starting to face is almost everyone is building agents that roughly look like the one I just fully fast forwarded. And you start with your front end, back end, and worker. You give it memory. You go spend a lot of money for NVIDIA inference, and then you start writing tools. And there's a couple of notes that I always mention. Do not pass the access token to the LLM. It should never have access to a credentials that's in plain text in the inference space. But that does happen, and we have seen scenarios where it either got privileged credentials or it just got keys to another thing, and it just ended up making the call. What also happens is every single time folks are trying to write a tool, they have to custom write each and every tool. And MCP has solved this to a large extent. But still, if we are looking at internal APIs, a lot of internal APIs are not really protected with user credentials or any credentials. And those tools end up being very, very root privileges, as well as they can do damage. Like in one scenario, there was a database vendor who had a agent that was configured with the same credentials as support. You could social engineer the agent into giving you access to someone else's tenant. So those are actual problems. And what we're trying to solve here for first phase is we're recommending that instead of trying to build the tools, abstract the authorization and especially token delegation part out of the tool calls and abstract it as like maybe one function. So one of the things that we are recommending, and this is all OAuth, right? So all of my demos use OAuth themselves, and we have some syntactic sugar for it, but this is just token exchange. So what Auth0 can do in this scenario, and I glanced over it very quickly, but I'm going to break this down for now. Auth0 can connect to any of the previous, like on the left-hand side, any of the identity providers. And these all issue credentials that are on behalf of the user. We can also facilitate delivering them on the other side. And if you're using any OAuth OpenID Connect compliant identity provider, they can all manage credentials for you. What this means is if you're writing an agent today, it's much easier to offload that token, the part of obtaining delegated access, as well as granting access to an authorization server. And so in the demo, which I'm going to switch back to. What we had done is the stock app itself does not actually live in the same tenant as the stock API. So our trade agent lives in a completely separate tenant. And what we had done is we had added a enterprise, or it's called enterprise, but it's just a connection. What we had done is we had given it an upstream identity provider. Okay, so what we did is we went to the OpenID Connect, and what we did is for the stock API server, for this agent, we actually created a connection in Auth0. So this has the root credentials, well, the root identity provider, which is stock.workshop.us.auth0.com. We added an authorization endpoint for it. We added a token endpoint for it. It has its jocks. And we configured the scopes we want access to. If I click the try button here, what it actually does is it makes a request to the upstream identity provider. So I'm on stock workshop, Shrek stock workshop, and not the GenAI tenant that I was using. The second half of what we've added there is we add support for this token vault. So when we obtain a refresh token, we'll keep the access tokens managed for the application. So in case when I do something like, can you fetch my portfolio? Behind the scenes, this agent is actually asking Auth0 for an access token to call the stock API, and then that makes the actual call to the stock API. And what I'm going to do, because my demo has been going all over the place, is I'm going to just log the token so that we can actually look into what exactly is happening. So if I go to console.log, token, and now I'm going to refresh and make it do that again. Hey, can you fetch my portfolio? So if I go back to the console, if I take this access token, there are a couple of things that I want to call out. It was issued for api.stocktrade.example. That's not an API that exists in this identity domain. It's an upstream identity provider's API, which only exists for the stock provider. So in this scenario, the agent has no access to the API without being explicitly granted. And two, it was issued with very specific scopes that allow very specific permissions to the agent. Consider a scenario like this one, where if I had told the agent to go monitor my stock, in order for this to work, the agent can tell me like, yes, I'll do this, and it can continuously keep pulling the stock. Or what it should do is it should start a worker thread. In the worker thread and the front-end application are not the same thing. There is a security boundary that you're jumping between the worker and your interactive client. It will now keep calling the stock API every now and then. If it sees some stock has dropped, it will try to make a sell transaction. At which point, the stock API might respond with, this is not good enough for me because I don't like the fact that you're trying to sell a stock and I've never seen this IP, or this just looks suspicious. This is a pretty common scenario that happens in banking transactions. Most of us get like that confirmation code. At this point, the worker has to now request human approval. But when it does so, that human approval cannot come from the worker, because the stock API cannot just trust the worker. This needs to be independently validated between the stock API and the worker. And so in this scenario, CBA is one way to do this, but there are other OAuth grants that also become available, where what you could do is you could go from the worker and request approval to the stock API, and the stock app would connect the dots. And those are the things that I wanted to kind of like highlight, but since my demo is like halfly working, I'm just gonna go over them in parts, right? So when we added the portfolio tools, this is roughly what happened. I ask it to do something, It goes, gets the token from the token vault, it calls the vault API, and it returns. At this point, the exchange is governed through on behalf of, but behind the scenes, auth0, if the token had expired, would have actually ended up calling the other tenant or whichever OpenID Connect provider we had. And what this allows us to do is, in the end, the credentials never leave a secure storage system, and they're always available wherever you're using them. We start with something like this, right? Where the stock scenario, and I've gone through it already again and again. Everything is first party here. In the example that I just gave for StepUp, most banking apps do that. The challenge becomes when you want to do it for MCP, but the same flow also works for MCP. So imagine if this was Claude code, or Claude in general. Claude could obtain a token for the MCP server or the stock mcp.stock.example. And when it needs to go ahead and call the backend API, it can then itself try to perform those transactions. And because your MCP server is something that you control, you can write first-party code there. So in case of the CEBA grant, you can't really trust the agent to be truthful. But this was modeled as an MCP scenario. Your MCP server could actually make the call to the identity provider to actually delegate this. And that also works for any APIs. This is a pretty common OAuth standard, which is known as on behalf of. And roughly what it does is on the stock MCP server, you ask for a different audience, and you exchange it. And so you can keep cascading them until you have the assurances that you need. I'm really sorry about the workshop just not working, and I was hoping to do certain things, but I think I can actually Q&A at this point.
So basically, if we have an API key, we can always code in to make our own MCP server standard for ourselves, right? So we customize it. So we can save our MCP server in my container or in my cloud. Will that we still have a risk? And what's the limit if I do it this way?
Are you talking about local MCP or remote MCP in that case? Are you connecting it over STDIO or HTTP?
This is a good question. I'm not. Can you explain to that?
So MCP, if you're using something like Claude or if you're using VS Code, it can connect to the MCP server in two ways. One is it can start a child process, and then it's just talking over standard input and output. And the other is it can try to make an HTTP request, which is to another server. And then it's hitting over network. If you're fully running it with Docker in your own containers, that's very different than if, let's say, in an enterprise environment or something like mcp.github.com. That would be a shared public environment. So which is the scenario that you're trying?
Oh, I see. For example, I just give you an example, okay? For example, there's a 3D Blender platform, right? I have their API key. I use their API key. I just hard code it to create my own MCP server. So I save my MCP server on the cloud. So everybody can use this. Then I can use my MCP cloud to ask their API.
So in that case, if you hard code your API keys, how does it differentiate between if I try to access it or if he tried to access it?
Yeah, that is also, I think it's limited. I think we'll maybe give each person a different role. Each person have the different functionality to do it.
And in that also, even in that case, how does the MCP server know who it's talking to?
I'm thinking about also I can save it in the container, so I can give each person a role.
Oh, so in a web container, you have some kind of a provisioning where each person gets their own separate container?
Yes. How about like that?
That is a potential possibility. What I would recommend for that would be outside, it's not governed by OAuth, but then you're talking over you're trying to do it over. So MCP as a protocol also allows you to do custom transports. That to me sounds closer to custom transports where you have a dev container and you have some sort of a hosted environment that's available to only that person, right? So you have some kind of an enterprise managed system which fully separates out the MCP. Well, it fully abstracts out that he cannot access my MCP container. Is that what the assurance that you have?
That is also what I'm thinking how to do it.
So the way I would recommend doing it and the way we are doing it ourselves internally is in the enterprise world, there are two types of MCP clients. One is the one that you built yourself. So if you wanted to write an internal app for your own internal employees, you would know, you would have an identity provider, right? You sign in with Okta, you sign in with Azure AD, you sign in with any sort of like a corporate identity provider. You could leverage that identity provider to obtain a credential for them.
Yes.
And so that would be one half. The other would be if you're inside your enterprise, you have something like VS Code or Cursor or Windsurf. Either of these clients are no longer built by you. They are built by third-party companies that are trustable, but they're not like, you can't influence the source code there. And so for both of those scenarios, what we are recommending is you should model that as like an internal MCP gateway. So you have like a proxy MCP server, because the interesting thing about MCP is that protocol allows for you to add an entire additional MCP server in front of an MCP server, and you can combine it that way. It could be a transparent proxy, and there's a product called, I think, whataboutU.ai. I think they have a Unia. They have an MCP gateway. I think there's a STO proxy as well. And what all of these products do is they're trying to enforce this layer, and I'm just going to try to draw this. Well, I'm just going to walk. Did it work? No. Oh. So imagine like your internal workforce provider is sitting here, right? And what you probably want to do is, and this is just using Auth0, but it could just, even if it wasn't there, model would be the same. You assume that the AI agent is completely third party. And you always assume that the only place that you control is a first party MCP server you're writing. Now, this MCP server itself can call backend servers or other MCP servers. So what you can do is you can rely on your primary identity provider to issue you a token for this that only grants it access to the MCP. So the example would be, let's say I want to grant access to Jira. This is Claude, it wants to see my Jira account. When Claude makes a request to access Jira, this credential is only good enough for it to call your MCP gateway. From your MCP gateway to Jira, your first-party corporate identity provider can actually facilitate that exchange. And so that's one way to model it. That's something that we are doing internally ourselves because we have Token Vault. So we can just use Token Vault to almost ensure that all of OAuth credentials do not end up in the third-party client. And they're usually held either in the Auth0 Token Vault or some kind of a secure infrastructure. Maybe it could be closer to the MCP server as well. But that's how I would model it. Instead of trying to containerize it, because then you would need almost operating system levels of assurances. That way, even if this was any third-party client, you could then control that. And the second thing that the MCP spec itself might be going towards is, I don't know if you were following the MCP spec, but there is a new standard that's being pushed now, which is called the OAuth client ID metadata. Today, if this agent wanted to talk to this MCP server, it would have to register its own new credentials here. And this server has no idea who this agent is. With OAuth client ID metadata, this agent has a document that it hosts. So you could say something like allow VS Code, allow Claude, allow Cursor, but do not allow anyone else. And with those two, you would be able to get with that standard, you would be able to get enough assurances to protect your internal resources.
Thank you so much. That's really clear. Thank you.
I had a question. Thank you. I had a question about how much you can trust an AI agent with confidential data. So obviously you just mentioned that you should never give your credentials to an AI agent because they can be prompted, they can be whatever to gaining access to those credentials. But are there any techniques for, say, I don't know, passing encrypted credentials to an AI agent and then having the API that the AI agent talks to decrypt those credentials? Any techniques like that?
One of the simplest thing we could do, and again, that's my personal opinion, but when we're talking about MCP servers, they're net new. They do not exist, right? And so they have like this fresh new cadence of like writing software in a way that we have never done before. Because MCP servers require the protected resource metadata endpoint. If you're unfamiliar with protected resource metadata, it's a OAuth spec, which roughly translates to the server itself, whichever one is being protected by the OAuth client, gets to host a document that says who it's going to trust and where its keys are. Because you have that assurance now, especially the fact that it can host its own JSON web keys, it's now very, very, very easy to have a bearer token that's a JOT, but it's encrypted because we have a very clear way to get its public key. So we can always encrypt that at the token level. Beyond that point, limiting information by MCP is going to be, it's going to be a harder problem than just like, you know, redaction. And let me give you an example. Imagine if like some meeting was happening and you had like this document that had internal sales numbers and that was on the screen for 10 minutes. Your average salesperson would know that that needs to be redacted. And they might leverage that information to, you know, hint towards a more positive outlook to a customer, but they're not going to, you know, say the whole thing as is. That's a very blurry line which an AI agent cannot infer, right? Because it could, for it, it's just data. And it has consequences. So it needs to understand that this is a sales figure. Now, we can train, we can prompt, we can add redaction, but in case of sensitive data itself, depending on what that data is, what I would recommend is if it needs to go from your controlled assets to your controlled assets, use JSON Web Encryption so that at the very least the third parties don't see it. When it comes to returning data from MCP servers, try to limit it because it's context engineering. It's the best practice to reduce context as much as you can. You should be able to make tools that are slightly different levels, right? So you don't disclose someone's entire profile information. You only disclose maybe a one-way hash, right? Those are some techniques that you could use, but overall, depending on what sensitive data it is, like if it's someone's medical health information, I would not send that to an inference stack unless I control that inference stack, right? If it's someone's banking records, that's a different conversation. So do you have any specific scenario on that sensitive information?
No, I was just spitballing. Thinking about what might be an issue.
You could potentially use fine-grained authorization, something like Zanzibar or FGA, to limit the documents that people have, but I would be very curious to see how that grows into just inside a paragraph. There could be interlaced information. So I would be more curious to see how that grows, because you can't really redact per token yet. You would have to almost hand redact the document, and at that point it wouldn't scale. But when you're writing tools, I would assume that here, when you're exposing tools, don't just forward the API data as is, because your first-party clients tend to have a lot more information than they render. a lot of times when we'll talk to someone and we'll open up their access token, we'll see like people's addresses, because the first party client uses that address to give them a good deal. A third party client is going to use that for tracking, and that's information disclosure. So as we move more and more towards talking to third party clients, one thing the MCP server can do is, it's not going to be automatic, but at the very least, the newer tools and the newer resources allow us to limit what we're sending back. But once it's exposed, I don't think there's anything we could do in that case.
Gotcha. Thank you.
So this architecture you said you guys are using internally, right? But out there in market, is somebody already using it?
There's some, I think Anthropic itself uses an internal MCP proxy. So they have like an MCP library, which so if you want to talk to Jira, it will be internal://Jira. And that MCP library does very similar stuff, where all of the OAuth credentials and all of sensitive credentials are managed by their SDS or token cache. They're never visible to every single developer or every single tool's client, right? Because their way of modeling that is this internal MCP library almost forwards the MCP protocol for every single client. So the internal employee connects their access to Jira, and now any client they build, they just need to be able to add this library and leverage it again.
Going to the applications, and I think, linking with the previous question about, who would trust the new architecture, as in it's a new, idea right now. Some of the examples, I think you mentioned a good example with the stocks. I think healthcare reports would be another one. Is there any, platform, using this method for sharing that kind of sensitive data as of yet, or it's still under discussion, or?
It's roughly what Zapier does. Zapier is roughly doing the same, where you're connecting to Zapier, and then Zapier is connecting to everyone else.
Okay.
That's very similar, if I understood your question correctly.
Yeah. Just.
It's also like Pipedream does similar. It's like there's a lot of like MCP wrappers that are gonna offload like token minting or token vaulting, as well as API calling. But I think that there's a lot more work that needs to be done. But the closest example is like, let's look at how like ChatGPT or Claude themselves call APIs. If you go and sign into a ChatGPT integration, your access token is never on the ChatGPT client, right?
Okay.
The access token to Jira, if you're accessing ChatGPT through Jira, only lives within ChatGPT servers. So ChatGPT itself has a vault where they're storing your credentials. And that model works very well because there are two problems that happen if you try to make it go to the client. One, if you picked up your phone and you want to talk to it on your laptop, you don't have to authenticate twice. You only authenticate ChatGPT once. And two, if your phone gets stolen, your Jira credential also does not become vulnerable. In that case, even in the ChatGPT credential, which is the least privileged entity in that chain, is the only thing that's on your phone. So from a breach point of view, it also limits the blast radius, because what you will notice is, let's say there was something that stole your refresh token or access token, and it wants to do something malicious. That attack pattern would look very different than you normally using ChatGPT. So there's another additional advantage there too, because you're gating that token completely outside the untrusted client.
Yep. Thank you.
Well, folks, I'm very sorry about the finickiness of my stack, but I am available to chat about Auth and Okta and Auth0. We're trying to release several products. One of them is Token Vault that we talked about today, and I did a very quick short demo. I wish that we'd have done more code so it would be slower, but what I would love to do is I would love to hear the problems that you guys are facing when you're building your applications, especially when agents have to access data or agents have to access credentials on someone's behalf, or when they have to do sensitive operations, like the stock trade example. If it needs to sell stock, it must get human consent in some cases. Those are problems that we're going to see a lot more as agents touch more and more of the software we use today. Like today, there's only 79 remote MCP servers and about 6,000 local ones that you have to pass API keys to. I would assume that we would have 6,000 remote HTTP servers by the same time next year. And that means there are 6,000 services that can now talk to each other, because from one MCP server, you can talk to another, and the MCP server itself can be an inference client. So there's a lot of nesting that opens up, and I would love to hear if you're building applications that are into that space and how we can help. That's all from me for today.